of transactions that are relevant to the addresses that you own. The idea of fraud proofs is that if a full node downloads some transaction data and realizes that this data contains invalid transactions, then the full node can send the light client a succinct proof that this is the case. And the light client can reject that block header and move on to the next valid chain in the blockchain. So the original Bitcoin white paper actually mentions this idea called alert. It's mentioned as alerts. And alerts are basically messages that full nodes can send to light clients to alert them that some block is invalid. But this doesn't quite work very well because I can just launch a bunch of full nodes and send a bunch of messages to the same light client to tell them every block is invalid, and that would basically force the light client to download the entire blockchain, so that's basically a denial of service attack. So in the worst case scenario, this alert scheme, the efficiency of this alert scheme requires light clients to download the whole blockchain, which effectively is like running a full node. So it's not really that much better than running a full node in a worst case scenario. So there's also been some earlier work on compact fraud proofs, which is the idea that you could actually just have more compact fraud proofs for individual transactions rather than the entire blocks. But these early ideas of compact fraud proofs, they propose a different fraud proof for every single type of way to violate the protocol rules. So for example, you might have one type of fraud proof for a transaction that spends an invalid UTXO. You might have another type of fraud proof for a transaction that spends more money than it should, and you might have another fraud proof for a block where a miner has mined more reward than they're allowed to. But what we can do is we can actually improve on this and simplify the entire fraud proof system into one single fraud proof. So that makes it a lot easier to implement. So if you consider the blockchain is basically a state transition system, so you have some block X, and then you have block X plus 1, and then you have a bunch of transactions in block X plus 1, and if you apply all of these transactions sequentially, one by one, they change the state of the blockchain in some way. And you can imagine there's a state transition function that takes in the current state and a transaction and returns the new state or an error if the transaction does an invalid operation. So then what if one of these transitions is incorrect? Or what if one of these transactions are illegal? Then we basically need a compact way to prove this. So basically, there's this idea of committing to the state in the block header. So you can represent the entire state of the blockchain as a single Merkle root, and Ethereum and other blockchains already do this by using a structure called a Patricia tree. And the idea is that you can basically store the blockchain as a key value store. So with an account-based system like Ethereum, that's already the case. With a UTXO-based system like Bitcoin, then you would have to imagine that the keys would basically be the UTXO IDs, and the values would be 1 if the UTXO is unspent, and 0 if the UTXO is already spent or does not exist. So effectively, it's basically a Merkle root that represents the state of all the UTXOs that could ever exist in the system and whether they're spent or not. So more recently, sparse Merkle trees have started gaining popularity, and Ethereum 2.0 is actually it's called Serenity now. Serenity is planning to actually use sparse Merkle trees instead of Patricia trees. And the idea of sparse Merkle trees is that you can basically have it's basically like any normal Merkle tree, except that it's got an insanely large number of leaves. So you have 2 to the power of 256 leaves if you want to be able to represent every single SHA-256 hash as a key. And then if you want to look up that specific key, you basically hash the key and look up the corresponding index of that key in the tree. So like if the hash of the key is 1, then you look up the value in index 1, and that is basically the associated value with the key. So it's pretty simple, and it's much simpler than a Patricia tree, but it's as efficient, or almost as efficient as a Patricia tree, or as efficient as a standard Merkle tree, because the size of the Merkle proofs are still O log n, where n is the number of non-empty elements in the tree. So even though the tree has 2 to the power of 256 elements, you only care about the elements that you actually have any values in them. You don't care about you don't care about the leaves that have 0 in them. So it's still efficient with regards to how many leaves in the tree have actual values in them that aren't 0. And so then we can imagine the blockchain as a state transition system. So if we have these state Merkle roots, these sparse Merkle tree Merkle roots that represent the state of the blockchain, and all of the UTXOs in the blockchain or the account, then we can basically imagine that each transaction applied sequentially modifies the Merkle root of the state in some way. So you can see there's many intermediate state roots between block X and block X plus 1. And so we can basically use these intermediate state roots to create an execution trace of the blockchain. And if we put these state roots, if we actually include these state roots in the blocks, then we can basically use this execution trace. And then the state root transition system takes in the state root, the transaction itself, and the witnesses, which I'll describe in a moment, and returns either the new state root or an error. And the witnesses of a transaction are basically the Merkle proofs of the part of the state root or the state tree that the transaction accesses. So you can basically prove to someone that some transaction modifies the state in some way without that person having the entire state of the blockchain, which is really useful. And this is a concept called the stateless client concept. There's been a bunch of work on that. So then the Ford proof itself, if you have the system, would be fairly simple. It would simply consist of the pre-state root, the post-state root, the transaction itself, and the witnesses for that transaction, and also all of the Merkle proofs for all of those things being included in the block header. And then once a full node can send the light client all of these things, light client can pass these things through the root transition function and see if the resulting state root actually matches the one in the blockchain, and if it doesn't, then the Ford proof would be valid. Or if the state root should be an error, then the Ford proof will be valid, and then the light client could reject the block. But the problem with this is that there's a problem called the data availability problem. The problem is, what if the miner doesn't actually release any of the transaction data? What if the miner simply publishes the block headers or directly passes the block headers to the light clients, and the light clients will accept these blocks because they're in the longest chain, for example, and then full nodes don't have access to the transaction data, and then as a result, the full nodes can't generate these fraud proofs because they don't have the data to generate the fraud proofs, because the miner has withheld the block data and only released the headers. So we basically need a way to guarantee that data is available. So Vitalik has proposed a neat way to do this that is based on erasure coding. The idea of erasure coding is that you can take some data that is X pieces long, and you can blow up that data to 2X pieces, such that if you lose any X pieces of that data, you can recover the entire data from any remaining X pieces. So effectively, this no longer becomes a 100% data availability problem. This is now a 50% data availability problem, because you only need 50% of the data to have access to the whole block, or to be able to recover the whole block. And so that means if a miner wants to hide even a single byte in this block, or not release a single byte in this block, they would have to not release half of the block. And what we can do with this is we can build random sampling scheme to get probabilistic guarantees that the data is available. So if we assume that the miner is actually trying to do this attack and has actually withheld 50% of the block, then the light client can randomly sample different parts of the block, and if it lands on a part of the block that is unavailable, that the miner hasn't released data for, then it won't receive a response for that part of the block. And if it doesn't receive a response for that part of the block, then it won't accept that block into its valid chain. So if you make one sample, there's a 50% chance that you land on an unavailable on an available block. After the second sample, there's a 25% chance of only landing on available blocks. Then there's a 12.5% chance, and so on and so forth. So then you get basically you get very high probability guarantees that you will actually land on an unavailable block if the miner has hidden 50% of the block. And with this scheme, the clients should gossip the samples that they have received to full nodes if they ask for them. So if a full node only has a part of the block, then a full node might ask the light client for the samples that it might not have, and this would basically allow the network to gossip these pieces until the network has half the block, and once they have half the block, they can recover the entire block and generate these fraud proofs. But also the thing to note with the scheme is that you need enough light clients to be making enough samples to actually reconstruct the entire data. And we'll do some analysis on that in a moment. But the problem with the scheme I've described so far with this type of erasure coding is that, well, what if the miner incorrectly generates the extended data? What if the miner incorrectly generates the erasure code? Like, they could just insert gibberish or nonsense into the extended data of the block. And so that's a problem, because then to prove to a light client that the extended data is incorrect, then you have to basically give them the entire original data of the block, and they have to recompute that extended data to see if it matches or not, or if it's correct or not. And the efficiency of that is O block size. So that's back to square one with Satoshi's LLET system. So to improve on this, we can use multi-dimensional erasure coding, so you basically arrange the data of the block into a square, and then you can individually extend the rows and columns of that square to make a bigger square. And then the size of if the miner incorrectly generates the extended data, then the size of the fraud proof would be limited to a single row or column. So then the efficiency of the system, or the fraud proof, or the size of the fraud proof, would be square root block size, which is much better. And you can take this to higher dimensions. So in this scheme, it's 2-dimensional. You can go high. You can do higher dimensions, but there's trade-offs that I won't talk about here. So with this, the miner would have to hide around 25% of the entire square to make any part of it unavailable. And so if we look at the probability here, what is the probability of a client landing on at least one unavailable piece? The size is wrong, it should say unavailable piece. If the miner has hidden roughly 25% of the square. Because if the light client lands on an unavailable piece, then that means they have successfully noticed that the block is unavailable. And after 3 samples, it's pretty low, it's like 60%. After 15 samples, it's 99%, which is reasonably high. That might seem quite low, but actually, from an economic perspective, it's quite good, because that means on average, a miner would have to mine 100 blocks before they can trick an individual light client. You can also go high probability. So if you have 30 samples, you can get 99.99% probability. But I think 99 is good enough if you consider the economic implications of it. So as I mentioned, you need a minimum number of light clients to be making the sample requests. And also the other issue with this is that miners might decide to only release these pieces as clients ask for them. And if they do that, then they can fool the first number of clients that ask for these, because they can only release they might just release enough samples until they get to just 50%. And once they get to 50%, they can stop releasing samples. And so they've fooled everyone that already asked for the samples, but they can't fool everyone else. And here you can see the kind of numbers, and how many clients can be fooled depends on how many samples they make and how wide the square is. So with a 32 by 32 square, if you have 10 samples per client, then the number of clients that can be fooled is about 500. But ideally, we don't want any clients to be fooled, so there are ways to prevent that. Even though I don't think 500 is a bad number, because if you consider there's like 1 million people who have installed the Android Light Client or SPV wallet for Bitcoin, 500 is a very small proportion, but ideally still, we prefer that no one can get fooled, or everyone has the same high probability of not being fooled. And so if you consider that light clients can send the requests or the sampling requests anonymously, and then if they send them all at the same time or through a mixnet, so then we can assume that the order in which the network receives the sampling requests is uniformly random, so that effectively all of the requests are interleaved, then it wouldn't be possible for the network or a miner to selectively release samples to a light client, because they wouldn't be able to link different sample requests to the same light client. And so that would prevent the attack that I described in the previous slide. How much time do I have?
You've got another solid 10 minutes left.
Okay, so let's look at the security assumptions made by this system. So what additional security assumptions are necessary with different protocols, so that the clients can be sure that they're only accepting valid blocks? And note that this is very different. What are valid blocks is very different to what blocks are in the longest chain. So full nodes, for example, they validate the blocks themselves. So they don't have to make any extra assumptions to be sure that the blocks are valid, except for things like making like the operating system is secure or stuff like that, or that their software isn't compromised. But if you use the full node as the baseline standard, then let's look at what additional assumptions light clients make. So in this table it says SPV clients, but I'm using the words SPV and light clients interchangeably. SPV basically stands for simple payment verification, which is the type of light client that's specific to Bitcoin. So light clients, standard light clients, they assume that the majority of the consensus set is honest when to ensure that all of the blocks they accept are valid and don't contain any invalid transactions. Now, if we add fraud proofs to the light client, we can eliminate that honest majority assumption and replace them with 3 much weaker assumptions, in my opinion. So the first assumption is that there's at least one honest full node in the connected network graph. And I think that's a very reasonable assumption, because if there isn't at least one honest full node in the entire network, then you're not going to be on the correct chain anyway, and you're potentially being eclipse attacked. Second assumption is that there's a maximum network delay to receive these fraud proofs. So if you're a light client and you see a new block header, then you should wait a certain amount of time to see if there's any fraud proofs for that block header. And so if you assume that, for example, you wait 5 minutes, so with Bitcoin's block interval it's 10 minutes, and so if we assume conservatively that you can receive a fraud proof in 5 minutes, or it takes 5 minutes to send a message to the whole network, I think that's a very reasonable assumption, because if you have a network delay higher than that, then I think you have bigger problems, including you're going to have a lot of forks on the network. But I think the strongest assumption here is the last one, which is that you need a minimum number of light clients, like a few hundred of them. So as long as you have a network that is popular enough, so that's such that there's always a few hundred light clients running, and if it's sharded, then there has to be a few hundred light clients per shard, then that scheme should work. And I think all of these 3 assumptions put together are significantly weaker assumptions than 51% of consensus is honest. And this is, so in Bitcoin, in standard blockchains, that's not really a big issue. Like you can probably assume that there's honest majority. Like, for example, with Bitcoin's with Bitcoin because you can validate the blockchain itself, and it's unlikely that there's going to be a 51% attack that is going to actually try to steal people's money because there's so many people that are running full nodes that no one is going to be fooled. But with protocols that use sharding, then it's a really important problem because it's not about the entire network. It's no longer about the entire network having a dishonest majority. It's about individual shards having dishonest majorities. So like if you randomly sample from a greater set of nodes to assign those to shards, and then you have like 100 shards, and oops, in one of those shards you randomly sampled a dishonest majority, then that dishonest shard, that corrupt shard can poison all of the other shards with its cross-shard transactions and poison invalid state into those 100 other shards. So in the context of sharding, and also in the context of very high on-chain throughput, for example, through bigger blocks, it's very important to try to eliminate this assumption for light clients. I'm not going to go too much into the performance, but it's in the paper. But overall, everything is reasonably efficient. In terms of space and bandwidth, everything is in a matter of kilobytes. The biggest overhead is in the fact that if you're a light client and you want to be sure that you have assurances that the data is available, then you basically have to download a Merkle root for each row and column in this square, and so that adds a lot of overhead to the block header. So with a block header that doesn't include that, it would be about 128 bytes. But with a block header that does include these Merkle roots, it will be about 2 kilobytes, which is I think it's a reasonable trade-off to have guarantees that the fraud proofs are available. Oops. Yeah, in terms of computation costs, everything is also quite reasonably efficient. Yeah. So I'll take any questions. Thank you.
Great, thank you, Mustafa. Are there any questions from the audience to start with? Well, I have an immediate question. I thought it was really interesting.
Yeah.
You mentioned a paper. Where should I go to read more about this?
Oh, well, the slides were up. They were on slides. Let's see. Yeah, the link is here.
Great,
Yeah.
thank you. Because that's really interesting. So
Yeah.
do you foresee a future potentially where there will be lots of light clients using a security protocol like this and a smaller amount of full nodes?
Yeah, I mean, I think if you're going to do sharding, then I think it's absolutely necessary to have a system like that, because otherwise you're going to have a situation where corrupt shards can, as I said, poison the system. So this is something that Ethereum is actually thinking about as well. Yeah.
Great, Patty?
You mentioned that you need like 300 so light clients to run. Is that just for availability of the block, like to force the miners to give it out?
Yeah, you're right. So basically, you need a sufficient number of light clients to sample enough of the block, such that the whole block can be recovered from the samples.
Okay, and then if a light client doesn't receive that, they just discard it and don't accept it immediately.
Yeah, if a light client doesn't receive a sample, then it assumes that the block is unavailable.
Thank you. Your mic's coming. I'll just hold on to this one.
Yeah, just a quick question. You had 3 repositories listed there for the code.
Yep.
What are these individual modules? Which one to look at for what functionality?
So there were three repositories. One of them was by implementation of a sparse Merkle tree. It's not a very efficient implementation, but it works and it has high test coverage. And there's also implementation of a Reed-Solomon of the Erasure coding data availability scheme. That's I think production ready, so you can import that if you wanted to. And finally, there's an actual prototype of the fraud-proof system. All of it is written in Go, by the way. Yeah.
Thanks.
Excellent. Well, if there are no further questions, then
there
we'll...
was one there, I think.
Oh,
Yeah.
sorry. It's Sunday morning.
So in the context of when a light client receives an invalid or doesn't get the proofs, can they somehow make it request and slash the consensus mechanism if they do not provide data availability?
If the miner does, if the miner doesn't provide.
Yes, slash if data is not available.
So you can't actually do that because the problem with people have proposed using economic incentives or punishing people if they don't publish blocks, but it's not really possible to do that because if some data is unavailable, then that's a uniquely unattributable fault. It's like you don't know whose fault it is. Like it could be your fault because your network is poor, or it could be their fault because their network is poor. Yeah.
Sorry, I was just thinking, like, maybe can you have like a weird situation where the light clients reject it, but the other miners don't? Because maybe the miners don't share. Like, if I send it to another miner, maybe they don't share it on the network.
Well, I mean, in theory, miners should be running full nodes, or what miners are full nodes. So, if a full node should download the entire block. So, if a full node rejects the block because it's unavailable, then in theory, a light client should also reject that block. So, I don't foresee a situation like that happening unless all the miners are actually running light clients.
Okay. They were at one point. They were SPV mining.
Yeah, I mean, then in that case, I think you'll still be fine, even if the miners run light clients, because as I said, there's for each individual light client, there's very high probability of not being fooled. So like maybe you can trick 1% of the consensus. Yeah.
Great. Well, I think that is all we have time for to discuss this particular topic. Thanks. You, Mustafa. I will be calling up the next speaker then. Her name is Eva Sita. She is an assistant professor at Trinity College in Connecticut, and she's going to be talking to us about distributed randomness.
Oops. Hello, everyone. My name is Eva, and today I will talk about public randomness. This is a joint work with a team from EPFL, Yale University, and University of Bonn. So my talk will consist of 4 parts. I will first motivate why we actually decided to look into public randomness. I will tell you about 2 protocols we propose that target 2 very different deployment scenarios. I will tell you a little bit more about implementation, our results, and our current deployment. So let me tell you what public randomness is and why generating it is actually quite hard. So public randomness is very different from private randomness we're all used to. We typically use private randomness to generate our private keys, for example. Public randomness, on the other hand, is collectively used, right? We want that public randomness to be unpredictable ahead of time, but at some point when we're ready to use it, we'll reveal that, and it won't have to stay secret past that point in time. And clearly, when it comes to public randomness, entropy is not enough. Just the quality of randomness in terms of entropy won't get us where we want to be. So what do we use public randomness for? Turns out there's a number of applications of public randomness. We use them for random selections. You can think of lotteries, auditing elections. You can use public randomness for decks and team assignments in games, crypto, challenges in zero-knowledge proofs, authentication, nothing up my sleeve numbers. And lastly, protocols, something that is probably most relevant to you guys. You can use public randomness for sharding, as it's done on Ledger, that you will hear about right after my talk, but also for leader election in consensus protocols for proof of stake. So unfortunately, while it seems that public randomness is an easy concept, we've had a number of examples of failed or rigged public randomness. For example, in the Vietnam War lottery, dates representing birthdays were not sufficiently mixed, so if you were born in December, you were more likely to be drafted. Hot and cold balls were used to rig European soccer competitions. They would pick a team based on how the ball felt to touch, not something that anyone could be able to see. And lastly, an insider hacked a pseudo-random number generator to predict numbers or pick numbers in the Megabucks lottery. Then he tried to anonymously purchase a ticket with those specific numbers and collect a reward. The problem here is that because of a good lack of mechanism for public randomness, we can't implement fair and good public choices. And it turns out that public randomness is not a new concept. There has always been a need for it, and perhaps many years ago, a big book of numbers published by a reputable source was enough. Today, it's not. Today, we face two issues of trust and scale, and in this work, we addressed both of these issues. So we set out to achieve a decentralized public randomness in the very well understood and familiar to most of us threshold security model. We had 5 specific goals in mind. First, we wanted availability. We wanted to ensure that we can successfully complete the protocol even in the presence of faulty nodes. Unpredictability is needed to ensure that output is not revealed prematurely. We wanted to be able to tell exactly when parties will receive randomness. Unbiasability, we want the output to be distributed uniformly at random. Verifiability is something extremely important to public randomness. We want everyone, not only those participating in the protocol, to be able to check the randomness. And lastly, scalability. We wanted to run the protocol with potentially hundreds of participants. So there are 2 main approaches to public randomness, those that require trusted third parties, such as NIST randomness beacons, and those without it. The ones without it include Bitcoin, slow crypto hash functions, lotteries, and other data. While those do work, they often rely on new, unusual, or not fully believed assumptions. The 2 approaches that share our threshold security model include coin flipping and DKG, distributed key generation. They do work, however, they don't scale well past maybe tens of participants. So on the surface, it seems that generating public randomness is easy, right? You can simply take random inputs from all participants, and there's this full assumption that so long there is one honest participant, that will sufficiently randomize the output. Unfortunately, it completely doesn't work because the last node has full control of the output. They will simply wait to see what other inputs are and will pick their own input as a function of it. So we achieve no security. We can address this issue with a commit and reveal scheme, right? Where we have everyone choose their input up front before seeing anything. Unfortunately, a dishonest node can refuse to reveal their share upon seeing what the output of the protocol is going to be. If they don't like it, they can force a rerun, and that constitutes a bias. And this availability issue can be addressed using secret sharing, such that we can recover those inputs even if the adversary is not cooperating with us. The problem here is that the adversary can set bad shares, let's say to some honest nodes, and that means that not every node, honest node, will recover exactly the same random value. So this brings us to RunShare, asynchronous leaderless protocol that basically uses verifiable secret sharing to force all of the nodes to distribute consistent shares. While we do get availability, unpredictability, and unbiasability, we still don't have public verifiability and scalability. And we wanted to improve on these 2 goals. So that's exactly what was the goal for the 2 protocols I will tell you about, RunHound and RunHerd. They both achieve all the 5 properties in slightly different ways because they're meant for different deployment scenarios. So the goal of RunHound was to provide public verifiability by third parties and, of course, improve on the performance of RunShare. RunHound is designed to be a client-server protocol where the client is using a potentially large set of servers to scavenge randomness from. The beauty here is that the servers are nearly stateless. They're simply used by the client, and the client can be used different servers from run to run. We have a config file that is announced in advance, and with respect to that config file, we're gonna is it okay? We're going to run our protocol. So imagine a scenario where you have a lottery authority and they want to pick a winner in a fair and verifiable way. Such a run is typically announced publicly in advance. Then the lottery authority would be a client in our protocol, and they would use a set of independent parties to aid them in generating this randomness. The output of the protocol would be the chunk of randomness that we need to pick a winner, as well as a protocol transcript that will testify to or attest to the correctness of that randomness. So how do we achieve public verifiability? We do it in two ways. First, we use PVSS, publicly verifiable secret sharing, that improves upon regular VSS by adding encryption and zero-knowledge proofs. This means that anyone can look at the shares and anyone can check the shares without actually getting access to them. We also use collective signing to hold the client accountable and allow client to make a decision and publicly commit to that decision. Collective co-signing can be implemented using an aggregate threshold or multi-signature. In our implementation, we use Schnorr multi-signatures. So what's going to come out of the protocol again is the randomness and the transcript of the entire protocol run, because of this interesting property we have here that the client communicates with the servers directly and none of the servers talk to one another. This means that the client gets the entire view of the protocol, every single message that is sent and received and is needed to replay the protocol for verification. So scalability, right? I said we use PVSS. However, sharing with everyone is expensive. In my scalability goal, I told you that we want to run this protocol with potentially hundreds of participants. Sharing with everyone is simply too expensive. So the idea here is to shard the participating server into PVSS groups, then have every single group produce a secret, and have our randomness to be a function of all groups' secrets, right? The question here is how to securely assign participants to the groups, right? I told you that this is a randomness protocol, and most of you would tell me that the best way to do the sharding is randomly, right? So how do we address that problem? Well, it turns out that it actually doesn't matter if the client picks the groups in an arbitrary way. If we look at a client putting together those groups in terms of availability, right, the client can self-DOS itself if he puts human and malicious nodes into each group. However, for security, making sure that the outcome is unbiased, this is completely irrelevant. Due to the pigeonhole principle, we know that regardless of how the client assigns nodes to the groups, there will be at least one group with higher than average number of honest nodes, right? And that will be the group that holds a secret that the adversary cannot prematurely get access to and bias in any way. We also use collective signing, as I mentioned, to commit client to his choices, so he cannot play backsies and go back and say, I don't like this randomness, let me try something else. So let's briefly step through the protocol so you get a better idea how it works. First, the client puts together a config file that includes the names and the public keys of all the participating nodes, and also that's where the client assigns every node to a group. Then each node finds its group members. They pick their own secret, and they secret share using PVSS to only their group members. The nodes then take those PVS shares and send them back to the client. They also start the phase one of the collective co-signing. I mentioned that we're using Schnorr multi-signatures, so we have to do commit, challenge, and response. They're basically starting the process early on to certify the client choice later on. So the client will sit there and wait for those PVSS shares to come. He will verify them, discarding any shares that are not correct, right? And once he has sufficiently many shares from every group, he will decide which inputs from every group should contribute to that group's secret. Notice that we're doing that without knowing what the secrets are, right? We only have PVSS shares. The client will respond with the selection to the nodes and also with a commitment for the collective co-signing. All the servers will verify that the client's choice is valid, that the client picked at least F+1 inputs from every group, and they will produce their cozy response. They will produce their partial acknowledgement that they checked the choice and it's okay. The client will then wait for those responses to come. Those responses will be aggregated into a multi-signature. And once the client has 2F+1 of those acknowledgements from participating servers, he will take that multi-signature, send it to all the servers, and ask for decryption of their secrets. Each node will verify that, again, at least 2F+1 other nodes approved of the client choice, and they will start the process of sending the client the decrypted input values. The client then will simply gather the input values from every group. It will reconstruct each group secret, and then, in turn, the collective randomness, which is simply a function of every single group input. As an output, we're going to produce that randomness as well as the kind of log of the entire protocol, which consists of every single message that can be checked by anyone. Remember that the servers are stateless. The only state they hold are their private keys. So what do we achieve through this protocol? Well, we get all 4 properties, including public verifiability, and the complexity is acceptable. It's linear in the number of nodes, assuming that we're sharding into constant groups of size C. So far, I told you a protocol that is giving you randomness on demand, and the protocol is run by a client who is fully in charge and fully responsible for it, right? That doesn't kind of fit every deployment scenario. So our second goal was to kind of create this randomness beacon, a protocol that will give us a series of random values kind of in more continuous way. Specifically, we also wanted to improve on the public verifiability, both in the time it takes to do so and in the size of the proof. Ideally, we wanted it to be a single Schnorr signature to have a constant verification time. And of course, we wanted better performance because that's what we always want. So we built RunHerd as a randomness beacon. RunHerd is built upon a collective authority, which is basically a bunch of servers working together in an efficient and publicly verifiable way. RunHerd relies on a leader. However, leader is only trusted with availability. We're not assuming it's honest, we're simply assuming it's present, right? The leader simply coordinates the run among all the other nodes. So the main idea behind RunHerd was to create our collective randomness at this continuous stream of collective Schnorr signatures on some value. The benefit of that was definitely a small proof size. If you have a single signature, the size of it is small and the verification is quite small. And we wanted to get a better performance. So the problem here was that while it works, we achieved the goal of better performance because we're communicating on a tree, so it's log n, and the fact that the signatures are easy to verify, we weren't completely bias resistant. If we simply take every single node and we expect every node to always produce the value, then things really don't go well if one of the nodes is offline intentionally or otherwise. Because of one missing input, the resulting signature would be different, and that would give the adversary the ability to selectively affect the randomness that comes out of the protocol. So we had to address this availability issue, which we did by using threshold Schnorr signing. Threshold Schnorr signing allows you to create this multi-signature with only T out of N no presence, right? So we were able to tolerate some failures. We kind of arrange nodes in groups, right? Every group is producing a signature so long T nodes are present. So we are able to tolerate a fraction of nodes being unavailable in each run. And RunHerd has 2 main components. Setup, that is run once, is pretty expensive, but afterwards we're able to produce randomness in a pretty efficient way. So setup, we simply want to securely assign nodes to groups and kind of bootstrap the entire process. Setup is followed by many, many rounds of randomness, and it consists of four steps. So first, we pick a temporary leader. We can do so by simply picking someone with the lowest ticket generated using a VRF. That node would simply be a leader used for the initial step, just the bootstrapping of the process, not the leader who is later on responsible for randomness generation. That leader would actually use our previous protocol, runHound, to get a chunk of good randomness that we're going to use as a sharding seed. So this temporary leader plays the role of a runHound client, and the other servers participate in the usual server role. And that seed again is used to shard participants into groups. And notice that this assignment is not biased because it's done using unbiased randomness that came from the other protocol. Once we have those groups kind of assigned, we need each group to produce their collective group key. So every group has this collective key that they will be using to produce some output out of that group. Then we take all of those keys, we combine them together, and this becomes this collective runHerd key under which we'll be issuing those continuous collective signatures that will serve as our randomness. That collective key is certified by all servers in a run of collective co-signing, which means that we can discard the protocol that the transcript that comes out of runHound and simply have this key endorsed and believed by third parties. So how does randomness generation work? Once we do the heavy lifting in the setup phase, randomness generation is actually pretty easy. We simply have the authority leader, again, used, kind of picked using this unbiased randomness, broadcast a series of timestamps, and each group will simply produce their individual signature on that timestamp. The signatures will be collected and then combined together, and that will be our randomness. So notice that what we're achieving here is this ability to simply push some value down the communication tree. Every group produces their small signature. We take the signatures together, and comes our randomness. And that gives us really, really good verification, right? Because runHerd produces a single Schnorr signature, then anyone can efficiently verify the pair that comes out of the protocol under the collective runHerd key. It's constant time and really, really small size for the signature. So in this case, runHerd allows us to achieve all the properties we set out to achieve, including reasonable performance. Performance is logarithmic in the number of participants, again, under the assumption that we have a constant group size, C. So let me tell you about our implementation and where we are when it comes to deployment of our randomness beacon. So we implemented both protocols in Go using the DD's lab crypto libraries. We run experiments on the Terra lab using 32 physical machines, and we of course restricted network conditions to simulate more real-world conditions. So we looked at the randomness generation and verification time in runHound. We run our experiments up to 1,024 nodes in groups of varying sizes. So as a takeaway, in runHound with 1,024 nodes in a group size of 32, generation takes around 290 seconds and verification takes 160 seconds. We also looked at the CPU cost for both the client and the servers in exactly the same setup. And the total cost for one runHound run is around 10 CPU minutes, which translates to change on EC2. And again, that was done with 1,024 nodes with groups of 32 nodes. For RunHerd, we only looked at randoms generation time because verification is constant, so there was really no need to look into that. And as a takeaway, a generation for RunHerd takes around 6 seconds, but that after one time setup of 10 minutes. And those 10 minutes, again, are coming from the fact that we have to run RunHound first to get this good chunk of randomness to bootstrap RunHerd. I would like to tell you now about the actual deployment of our randomness protocol. It turns out that a lot of people are quite interested in public randomness. It turns out it's a pretty useful primitives to have. So we wanted to have a distributed version of this kind of randomness as a service. We called it DRAND, not very creatively, but gets the job done. And it's available on GitHub. So what DRAND is actually a protocol that implements the logic of RunHerd in a slightly different way. Again, RunHerd kind of implement as DRAND has a setup phase and then randomness generation. In setup, we're actually using threshold distributed key generation such that we can create this collective key under which we'll be issuing signatures that, again, will become our randomness. It's a threshold scheme which allows us to produce those signatures only when just a fraction of the nodes is present, right? And what comes out of this distributed key generation protocol is one collective key known to everyone and kind of secret shares of the private key that are held by individual nodes. But the entire secret private key is not known to any single person. The beauty is that we can also refresh those shares of a private key, which kind of allows us to deal with churn, right? It's kind of unreasonable to assume that the set of nodes running DRAND will never change. So this way, they can join the network, they can leave the network, and without changing the overall public key. So randomness generation is done using threshold BLS signatures, which gives us very good performance because it's a single round process. So we start by signing a fixed seed that is agreed upon at the beginning of the protocol, and then we continuously sign the output of the previous round. The beauty here is that we follow this kind of 3-step process of requesting a partial signature, waiting for T responses, reconstructing it, and then be able to immediately go to the next phase. And that also means that we don't even have a leader that is trusted with availability. Every node simply can wait for the T-shares on the network. The second they have them, they reconstruct randomness, and they issue a partial signature for that value. This also means that we can work in a synchronous setting. So where we are with the deployment? We actually have implementation in Go. It's open sourced. Our aim is to kind of have a very simple system to use, both to kind of participate and also for the users. Ideally, we would like it to be a one-step command where you can just fetch randomness the same way you can fetch current times for NTP servers. Deployment, we're currently working with NIST, Cloudflare, EPFL, of course, Kudelski Security, and hopefully others to run those distributed nodes all over. Kind of, we would like to have a node in every jurisdiction to kind of make not only the protocol trustworthy from the design point, but kind of have them all over the place. If you are interested in running a DRAND node, do talk to us. We make it super, super simple for you to do that. So let me conclude and say that public randomness is extremely important. Unfortunately, we face issues of trust and scale. We propose 2 protocols in the threshold security model that achieve the 5 properties we identified as necessary for modern uses of public randomness. We have an open source implementation that I encourage you to have a look at. And with that, I'm very happy to take questions.
Thank you, Eva. That was really interesting. I'm always astounded as to how much thinking goes into generating unpredictable randomness on demand, and I'm really glad to see that you're moving towards offering this as a service. So that headache can be solved for a lot of people.
Well, that's the plan.
Yeah, so really interesting. I have some questions at the back. Perhaps we can start with the gentleman over there.
Yeah. How does it? What actually happens when the malicious nodes exceed your threshold?
When they exceed the threshold, well, if they do, right, then they will recover all of this, at least all of the secrets from the groups, and then they can predict the randomness.
Can they control it?
So depends, right? Depending if we are looking at Runhound or Runherd, right? In Runherd, you kind of commit to the choices beforehand. There's this kind of intermediate run of collective co-signing. So really depending on kind of at which part of the protocol. If from the very beginning they control the majority of every single group, then all bets are off, right? Then they collaborate together, they pick whatever inputs they want, and comes out the output. But again, for kind of in both the protocols, we only need one group not to be controlled by the adversary, not all of them. All of them is for availability or liveness when it comes to a safety single group. Mm-hmm.
Yeah, so I was wondering...
oh, I'm sorry.
Yeah, how could you envision this working in a decentralized system? So like, let's suppose that we wanted to use this for proof of stake, for example.
Mm-hmm.
You need randomness proof of stake. That might be a chicken and egg situation because you need, if you want to randomly choose the, how do you choose the sets of participants in your protocol in a random way? And if you choose it with proof of stake, that might cause a chicken and egg situation because proof of stake needs randomness. And also, like, do you think that maybe the authority of the leader groups could be replaced by a smart contract to get rid of that availability assumption? Because if you have that availability assumption, then if you elect leaders and they go offline, they could potentially bias the randomness by refusing to participate if the randomness is not in their favor.
Okay, so there's a bunch of questions, right? So to start with, right, how to pick those nodes that participate, right? Well, it's an open question, right? It's you could start with some. So the beauty here is that you can use as big of a set as you want, right? So you're not limited to just a handful of selected nodes. So if you really want, you can just let everyone participate, right? At least in the initial stages, if that's what they want, right? Your second question was about kind of the leaders and them being able to bias the output. They're not able to bias the output. Even if they don't, they refuse to participate, right? They're simply, they will stop the protocol early enough, right, that none of the random choices will be out. And if you look at DRAND, right, DRAND is run in a completely leaderless way. It's just this continuous, so long there are T active nodes, right, we can kind of make progress, and they don't have to be coordinated by a single leader.
Right. So what happens if the leader becomes unavailable? Do you have to elect new leader?
You do have your change.
Yeah. So my point is, like, if I'm elected as leader, I don't like the result, and let's suppose like 30% of potential leaders are malicious. They could potentially bias the result a bit.
But by then there's enough information propagated in the network that they can reconstruct that randomness themselves.
Right.
So it would just take a little bit more time. We'll do a view change, and then the next leader would reconstruct the randomness from the previous round. So would not do a rerun of the protocol, right? It would take us much longer to get the previous round's randomness. So yeah, so you kind of delay things, but don't bias things.
There's another question here.
Mm-hmm.
I may have just lost the point in there, but in Runhound, you said that the servers were not talking between them, right? Mm-hmm. So basically, you have the client; he sends the information to the servers, the servers generate the thing, and they send it, right? But what actually prevents them to talk between themselves?
So no, they're welcome to. If that's what they want, right? They're welcome to.
But that's the point. If you can bias other groups by just like talking between themselves.
Well, they would have to be malicious, right? If they're malicious, they absolutely can talk to one another, right? Kind of under our model, we assume that the malicious servers are cooperating together, right? Honest servers won't, and if they simply don't want to send the messages direct to the client, they want to gossip it, that's perfectly fine too, because we're using PVSS, Evershare is encrypted, so even if it's you can put it on public blockchain for
even if there's a malicious participant in every one of the groups, is that right?
Yeah, because so every group has a number of nodes selected from it to contribute to that group's randomness. Even if you have a certain number of dishonest nodes in that group, they will only reveal their own inputs that contribute to the output of that group. They won't know the other inputs, right? So they will not be able to control the output of that group. That's exactly in RunHound. We need one of those groups collectively to be honest, not each individual node. So long that happens, the whole thing cannot be biased.
Right, cool. Thank you.
Yeah, thank you.
One more question. So, did you guys think at all about having nodes appear in shards appear in multiple shards to increase the probability of having one honest group?
Yeah, that's actually, it's problematic, right? But because you also, you increase the probability that dishonest nodes will appear many times, right? So it's much harder to reason about applying the pigeonhole principle that ensures, that guarantees, in fact, that one group will exist. That's definitely something you can, we looked at, but it turns out that we can't have this, hard guarantee of one group for sure will be uncorrupted in our model.
Excellent. Okay. Thank you very much, Eva.
Thank you.
I will now introduce our next speaker. His name is Filip Jovanovic. He is from the École Polytechnique in Lausanne, and he's going to be talking to us about OmniLedger and sharding.
All right. Thanks a lot. Yeah, so good morning, everyone. So I will present our project, OmniLedger, which is a secure scale-out decentralized ledger, and we achieve that via sharding. So this is a joint project between quite a few people, and some of them should look familiar to you because they also presented here or gave workshops. So this OmniLedger was designed by Lefteris, Nicolas, Linus, Eva, and Brian, and myself. So my talk is structured like this. I first will present some motivation on why we actually want to do sharding. Then I will introduce OmniLedger, our proposal. Then I will go over our implementation and evaluation of the system, and finally conclude. All right, so to motivate, I have a question to you. So what are we using blockchains for, or what are people using blockchains for? ICOs, yes. What else? Gambling, yes, very good. So that's actually one of the big things, right? People like to do games on the blockchain. And a while ago, there was this game called CryptoKitties, which was deployed on Ethereum, which completely stole the whole system because it became so popular that Ethereum could not take the load to operate that game, right? So, I mean, that's a little bit of a half-joking example, but it shows very well on what happens if blockchains become more popular and become more widespreadly used, right? So we need really high-performant ledgers to support all of these applications and whatever comes next. So for that reason, let's have a look on what are the core problems on the scalability issue for current blockchain systems. So at the core of Bitcoin, there is the Nakamoto Consensus Protocol, which works roughly like this. You have miners in the network. They are connected to each other, and they mine blocks by solving these cryptographic puzzles. And here the yellow node is the latest miner that found the latest block, and he extended the Bitcoin blockchain. So this mechanism has several drawbacks. First of all, there is a huge transaction confirmation delay, at least in Bitcoin, where the time that it takes to solve these cryptographic puzzles and thereby publish a new block is at least 10 minutes. So that means if you, as a client, are sending a transaction to the Bitcoin blockchain, it takes at least 10 minutes until it appears there and you can see it as confirmed. Then the next problem, on top of these 10 minutes delay, you also have only a 1 megabyte block size, which, when you do the math, translates to roughly 4 transactions per second that the system can sustain. And to give you an example on what that compares to, 4 transactions per second is roughly the amount of throughput that an IKEA does on a busy Saturday. Another problem is that Bitcoin provides you only weak consistency, which means once the transaction appears on the blockchain, you still have to wait several blocks before you can be really sure that it stays there. Because in the last part of the blockchain, there can still, forks can still appear, right? So once you have up to once the transaction is 6 blocks down in the blockchain, the probability that the fork still happens is reasonably low. And of course the last problem, but we won't talk too much about that here, is that proof of work mining consumes a lot of energy to sustain all of that. So the proof of work mining you need to solve these cryptographic puzzles. All right, so now you want to think, okay, this sounds like a problem also in cloud computing, for example, right? Where people just throw more hardware onto the issue and then it scales better. But it's not so easy here. So, because if you add more resources to the network in the form of miners, for example, that doesn't change the fact that a block still takes 10 minutes to be published, and the block size is one megabyte, right? So that doesn't change anything on the latency or on the throughput on the long term. And also, it doesn't change anything about the consistency problems that I mentioned before. So what we really want from our next generation scalable ledgers is something like that. So the green line shows you Bitcoin. On the x-axis, you have the number of validators, right? So if you have n validators, Bitcoin gives you 4 transactions per second. If you have 2 n validators, Bitcoin gives you 4 transactions per second. If you have 5 n validators, the same thing. So it doesn't change anything if you add more resources. But from an ideal system, we want to leverage the additional resources that we have available in the network, right? So the blue line shows you what we actually want to achieve. With more resources, we want to get a linear increase in the throughput, ideally. So, and this is a property which we call scale out. So the throughput increases linearly with the available resources. So, and when you look through the distributed databases literature, there's a technique called sharding. And sharding allows you to achieve scale-out performance. So how would you take this from this classical distributed databases towards the blockchain world? You can imagine like that you group the validators into distinct subsets, and you assign your validators to do different blockchains. Here, the yellow and the green one. And then the yellow validators would validate the yellow transactions, and the green ones would validate the green ones. And thereby, you now doubled the throughput in the system. However, when you do that, you come up immediately with 2 questions. Namely, first of all, how do we assign these validators to the shards? And the second one is, how do we send transactions across shards, right? We want to be able that persons who have accounts on the green blockchain can pay people on the yellow blockchain and vice versa. Otherwise, the utility of that strawman system would be very low. So with those 2 questions in mind, let's have a look on what people have worked on before. So here you see 3 goals that we want to achieve in our sharded or in the next generation ledgers. So we want to have decentralization, of course. We want to achieve security, and we also want to achieve scale-out performance. In 2016 at CCS, there was a paper called A Secure Sharding Protocol for Open Blockchains, which introduced Elastico. And Elastico is here on the axis between scale-out and decentralization. So which means it sacrifices security. The problem with Elastico is that you use proof of work to assign validators to shards, but that's not unbiasable because miners can drop blocks and thereby bias basically the randomness. And also when you look into Elastico a little bit closer, you see that the failure probability of the system increases with the number of shards that you have, which you don't want, of course. So that's why it sacrifices security. Another system, which is called RSCoin, was presented at NDSS, which is called Centrally Banked Cryptocurrencies. And it's on the scale-out and security axis. So RSCoin sacrifices decentralization to achieve both scale-out and security. So you have a central coordinator that takes care of the sharding. And in RSCoin, you also do not have a BFT consensus mechanism that secures the blockchain. So there it might happen that a client who colludes with the coordinator can double spend in the system. Then on the decentralization and security axis is the system that Lefteris presented yesterday called Biscoin. And yeah, I won't say that much more here. So Biscoin has good performance, but it doesn't scale out, as Lefteris mentioned yesterday. So, and in this talk, yeah, I will present OmniLedger, which achieves all three of those properties. All right. So when we started looking into OmniLedger, we had the following goals, which are in two categories. We had 3 security goals here in blue, which is we want to achieve full decentralization, so no trusted third parties or single points of compromise. We want to have shard robustness, meaning that from time to time you need reconfiguration in reconfiguration events in your system. So, but throughout those times we want to keep the shards operational. We don't want that the shards go down and then you have to rebootstrap those shards, right? And we also want to have secure transactions, meaning, especially across shards, meaning that transactions commit atomically or they abort eventually. And then we also had 3 performance goals, namely scale out, right? So we want to have linear throughput, as I mentioned initially. Then if you have very high transaction throughput systems, your blockchain will, of course, grow also very rapidly, which leads you to eventually having storage problems, right? Because somebody has to store the entire history, so we also want to get better there. And also we want to have low transaction confirmation latency, right? So when I send a transaction, it should be immediately or like very quickly confirmed, and we don't want to wait for 10 minutes or more until it's sure that the transaction was committed to the system. So to further motivate, I will start with the Strawman approach, which we call Simple Ledger. Simple Ledger evolves in epochs, which are denoted here by E. And in Simple Ledger, you have a shard coordinator, which regularly issues a shard configuration. And then the validators take that configuration, check in which shard they are, start setting up the shards with their peers, and then once that's done, they can start processing transactions. So here in that example, you see on the top is the shard coordinator, then the validators. Once they have the configuration, they get assigned to one of these 3 shards, yellow, green, or blue. And once the setup is done, they start processing transactions. So that, of course, works. It gives you scale-out performance, but it has several problems, right? So first of all, the shard coordinator is a trusted third party. Then it also has this problem when the shards are reconfigured, the shards go down basically, and you need some time to rebootstrap those shards. There is so far also no cross-shard transaction support, so basically what we just generated are 3 different blockchains. Then we also have a few performance drawbacks, namely the Biscoin failure mode, which means that the original Biscoin system was using tree structures to get very high performance, but you have problems here when nodes which are high up in the tree go down, then you cannot communicate with the whole subtree, or you need to reconfigure that subtree, or even worse, if the leader goes down, then you need to make a few changes, which is also costly. Then, as I already mentioned, you have high storage and bootstrapping costs because Biscoin is a very high throughput system, so the blockchains there will grow very fast. And you also have a throughput versus latency trade-off, meaning that when you want to achieve good throughput, you need big blocks. But to communicate and process these blocks, this will take time, right? So communicating just a 1 megabyte block is much quicker than communicating a 32 megabytes block. But 32 megabyte blocks gives you much better throughput than 1 megabyte blocks. So, and we also want to get rid of that trade-off somehow. All right, so here's a roadmap how we go from simple ledger to omni-ledger in 6 steps. First of all, we will introduce randomized sharding. Then we will tackle the problem of secure system configurations to have no downtime during this reconfiguration events. Then I will introduce an atomic cross-shard transaction protocol. Then you enhance the failure resistance of Biscoin by having more robust communication patterns. Then we do something which is called blockchain pruning to reduce the size of the amount of storage that you need. And then we introduce a mechanism called trust but verify to tackle that trade-off between high throughput and low latency transaction validation. So I will here only talk about these 3 points. They are the most important ones, and also because of time. All right. So if you remember, in the very beginning I said, okay, how do we, there is this open question, how do we assign validators to shards, right? So, and we have basically 2 options. The first one is we do so deterministically, right? We say maybe, the first 5 nodes go to the first shard, the next 5 nodes go to the second, and so on and so forth. However, that's a problem because the adversary can totally predict that, right? And he can potentially position his nodes in such a way that he can corrupt an entire shard. And as Mustafa said in his talk, that's a very bad situation because then these nodes can corrupt the entire system through bad cross-shard transactions. So, but what's a lot better is we do so randomly, because then when we use unbiasable public randomness, the adversary cannot control or predict that assignment. So then the next question becomes, how do you ensure also the long-term shard security against an adaptive adversary, right? Once you've assigned your nodes, the adversary might have some time to corrupt nodes adaptively afterwards. So, and there the 2 solutions are basically you make the shards large enough, and you also periodically reassign the validators to shards, which are these reconfiguration events that I mentioned before. And when you do the math, then you see, which is depicted here in the graph on the right-hand side, on the x-axis you see the adversarial power, and on the y-axis you see the approximate shard size that you need. And for example, if you want to be resistant against a 25% adversary, you roughly need a shard size of 600 to be secure. So yeah, as I said, the challenge here is how do you do unbiasable, unpredictable, and scalable shard validator assignment? And our solution is we use public randomness. And here we combine a VRF-based lottery with an unbiasable randomness protocol. Namely Randhaut, that Eva presented in the previous talk. And if you remember, Randhaut needs a leader or a client basically to execute the protocol. He's there for coordination. So, but again, we cannot pick the leader deterministically because then the protocol might fail a bunch of times. So that's why we use a VRF-based lottery to pick from all the validators that are out there one person who becomes the leader. So then this leader executes Randhaut. Why are we doing this? Okay, now the leader might have been picked randomly, but this might still be a bad guy, right? So we cannot trust him fully to do the shard validator assignment. So we want to take the input of all the validators that are available in the system, and that's where Randhaut comes in, which does exactly that. See the last talk. And once we have the verifiable randomness, we can use it to assign the validators to the shards. Here again, we have a yellow, blue, and a green shard. All right. So then the next challenge was that we wanted to have a protocol for atomic cross-shard transactions. And to do that, we again look back into the literature on distributed databases, and there are systems which are called, or protocols which are called two-phase commits, where you have a coordinator and a bunch of servers. And the coordinator, so yeah, as it says, there are two phases in the protocol. First, you have a voting phase where the coordinator sends a query to all the servers, asking them, can you execute that transactions? And all of the servers reply yes or no. And then the coordinator collects the replies and checks if everybody voted yes, then he can tell them, okay, now please commit. And if there's one of them who says no, then you execute a rollback protocol. So that looks already promising. However, if you are in a Byzantine setting, then you have the problem that the servers can be malicious. So one of the servers can always vote no, and basically you don't have any liveness anymore in the system, right? So, but taking that idea further, what you then realize is once you have this shard assignment, random shard assignment, and you have a Byzantine fault-tolerant consensus mechanism within the shards, you can consider basically all the shards honest, right? So now you take it basically one abstraction level higher and consider your shards as the honest processes in the system. So to give an example here, which is basically this for the atomics protocol, which does these secure cross-shard transactions, you have an initialization phase where a client says, I want to execute this transaction. Here in the example, it has inputs in shards 1 and 2, and it pays somebody in shard 3, the yellow one. And then the client sends this to the two input shards. The two input shards lock the funds and send acknowledgements back to the client. The client collects all of these acknowledgements. And then if all the input shards could lock the funds, he can go to the output shard and say, here I have a proof that you can commit the transaction in the yellow shard. On the other hand, if one of the shards aborts this process, here in the example, the green one, he sends back an error. Maybe the client does not have enough funds in his account in the green shard. Then basically the client executes a rollback mechanism where he goes then to his input shard that already has locked the funds and says, please unlock my funds. And thereby he can reclaim the transaction inputs. And the last point that I want to mention is how you can deal with the throughput versus latency trade-off. How are we on time?
We've got another, I'd say 10 minutes.
Okay, good. Where we introduced this trust but verify transaction validation mechanism. So as I mentioned initially, if you have big blocks, you get high throughput, but bad latency confirmation, right? Because it takes some time to propagate the blocks and to process them. On the other hand, if you have small blocks, you have low throughput, but a high transaction confirmation latency because small blocks propagate fast and they can be processed very fast. So now we ask ourselves, okay, how can we manage to combine these two approaches, right? So and what we did is basically we introduced this mechanism where within a shard you have one big group of validators who are there for the verification of large blocks and for adding them to the blockchain. And you have a set of smaller subshards, here the green ones, which are the optimistic validators, and a client sends his transaction always to the optimistic validators. They check it against their current state and give them very quickly a feedback just on that transaction. And then they forward those transactions to the bigger subshard, which re-executes the transactions and sees and checks if it's valid according to the blockchain of the shard. And thereby you can see, okay, the client gets very quick feedback on his transactions, and the core shard can aggregate, batch those transactions together into very big blocks, and thereby he gets good throughput. So, and this is perfectly fine, because if you consider like you buy just a coffee with your cryptocurrency, then it's okay that you get a very quick confirmation, right? Because the chances that somebody is attacking you for, I don't know, €3 or so is very low. On the other hand, when you have a big spending, you might want to wait until the core validators have really revalidated everything and put the transactions into the blockchain. So coming to the evaluation, yeah, this slide might look familiar because that's like exactly the same one that Eva showed before. So we basically implemented all of that in Go using our authority framework, the Biscoin consensus mechanism. We also implemented the Atomics cross-shard transaction protocol. This is all based on the Kyber crypto library, the ONET network library, and the authority framework. And the DTOLab setup uses 48 physical machines. And yeah, they were very well equipped machines. So, and to get realistic network configurations, we artificially reduced the bandwidth and also put a 200 millisecond round trip time latency, which roughly models the round trip latency that you have on the internet. So the first thing we wanted to evaluate is, okay, does OmniLedger really achieve scale-out performance? And here you see a graph. On the x-axis, you see the number of validators and shards. And on the y-axis, you see the number of transactions per second that OmniLedger can execute. And as a baseline, you also see Bitcoin here on the low end. It does like constantly just 4 transactions per second. Versus when you look at OmniLedger, with 70 validators and 1 shard, you get roughly 440 transactions per second. If you double that amount to 140 validators and 2 shards, then you get 870 transactions per second, and so on and so forth. And when you look at the line, it's really gives you a linear throughput increase in the number of validators that you have. Then, on the other hand, we also wanted to look into the question, what is the maximum throughput that OmniLedger can give you? Here, again, on the x-axis, you see the shard size and the adversarial power. And on the y-axis, you see the number of transactions per second that OmniLedger can do. So if you have a very, very weak adversary, which, for example, only corrupts 1% of the nodes, then you can live with shards who are just like of the size of 4 nodes, and thereby you get like really, really high throughput. If you go to a more permissionless setting, on the other hand, for example, if you have a 25% adversary, you need a number of validators in a shard of around 600. And there you can see, you get roughly 2,000 transactions per second. And something in between, when you have a 12.5% adversary, you actually get more throughput than Visa is doing on average. And then the final question that we had, how does OmniLedger do with this latency throughput trade-off? So here you see, in the first row, you see just OmniLedger in a regular setting without this trust but verify mechanism, where you get, on the very right-hand side, with 600 validators and a 25% adversary and 1 megabyte blocks, you get a confirmation from the client within roughly 15 seconds. When you split that up and you do this trust but verify validation, you can check the next 2 rows. And here it improves already quite a bit. So to get a first confirmation, a client only has to wait 4.5 seconds. And then to wait for the consistency to the re-evaluation of the core validators, he needs to roughly wait 1 minute. But then you have also 16 megabyte blocks in your blockchain, which gives you very high throughput. And when you compare this to Bitcoin, this is quite similar. You have like first a confirmation. This is like as soon as the transaction is included in the blockchain, which takes roughly 600 seconds, which are these 10 minutes. And for consistency, you have to wait 6 blocks, which translates to 1 hour or 3,600 seconds for 1 megabyte blocks. All right, so thereby I want to conclude my talk. So I presented OmniLedger, which is a secure scale-out distributed ledger framework. We use sharding for unbiasable, verifiable randomness generation to assign validators to shards and thereby achieve linear scale-out throughput. We use this Atomics protocol to have secure cross-shard transactions. And we use a trust but verify mechanism for breaking this trade-off between low latency confirmation and high throughput. And OmniLedger, I didn't mention that so far, but it works for proof of work, proof of stake, or in a permission setting, whatever you prefer. The paper appeared at IEEE Security and Privacy earlier this year. Here is a link, and the code is available on GitHub. So now I'm happy to take your questions. Thanks.
Thank you, Philip. I thought that was really clear. We have a question right here.
Thank you. Good talk. I wanted to ask, does the number of shards need to be preset when the system starts? How do you move from 1 to 2 to more?
No. So you can do this adaptively because the system evolves in epochs, right? So and what you assume is you have an identity blockchain running where the nodes sign up their identities saying, hey, I want to be a validator. And if in one epoch there are a lot of nodes joining, then you can, in the next epoch, when you do the reconfiguration, just assign them to new shards or even spin up an entire new shard as you go.
Sergi.
Great talk, Philip. Just out of curiosity, do you need to choose if you're doing the trust but verify thing in the configuration, or can any node do it?
So that's good question. So that's either way. So you could imagine that this is a system parameter, right? When you set up the system, you just say, we always do trust but verify. Right. From a client perspective, it doesn't change much, right? Because if the system has trust but verify, and you don't want to just have the first confirmation, then you just wait for the second step, and then you just ignore it, basically, right? So,
all right.
Yeah.
Cool. Thank you.
Thanks.
Hey, do you have some information on the throughput for cross-shard transactions?
No, we did not do that experiment. That's a good remark. So, of course, if all of your transactions are cross-shard, then your throughput will go down, right? So, but for that, you would need, some kind of realistic data points, or you would need to come up with some simulation to do that, and we didn't do that experiment.
And another quick one: where do the 25% come from? Is it a bound, or why did you pick 25%?
So this 25% comes from the fact that the failure probability. Okay, I didn't mention that. So the failure probability from that with 600 validators is relatively good. So we had we fixed a target failure probability in our system that we wanted to achieve. And when you then do the math for the different adversarial powers, then you just, okay, I have 1%, 12.5%, 25%, and so on, and you just check what is the shard size. It was just from the mathematical analysis, so there was not much behind that. Yeah.
So thank you, Philip.
Okay.
Then if there are no further questions, we'll move on to our next speaker. His name is Jijie Ren, and he is from the Delft University. He's going to be talking to us about value-centric blockchains. Thank you.
Oops. Okay, thanks, David, very much for introducing. Today I'm going to talk about value-centered blockchain. As you read from the title, it's very similar to what Philip had just said. And so unfortunately, the content of this one is also very similar to a lot of speakers has already said. But I'm just kidding. It's not very unfortunately because I can safely omit some of the contents in these slides, so it may be shorter. Yeah, okay. Skip these slides. So sorry about the word of text shows on each slide because the animation is gone. Okay, so I actually was about to ask the same question that Philip was asking. So what is the main functionality of blockchain? What we use blockchain for? But my answer would be that we mainly use that for value transfers. And that is basically what Bitcoin used first design blockchain for. And then as of this moment, most of the blockchains still use this as the major functionality of allow value transfer. And to allow value transfer, there's something we basically let all node to keep a consistent state. And so it's also very fortunate that Mustafa has already introduced the concept of the state. So in most of in Bitcoin, in Ethereum, the states can be represented as just accounts and balances. And for UTXO, it's a little bit hazy at the first place why it is account and balance, but in fact it is also account and balance. So all nodes need to keep a consistent state, and the blocks are simply the inputs, which is the states, the transition from one state to another. And what we are trying to do is, yeah, there is something, because it seems to be my old slides. Wow. Okay. Let me see, where am I? You have your new slides, or? Excuse me? You have your new slides. I have my new slides in my laptop, but it seems to be the old one, so I need to kind of find where am I. But sorry if my speech is a little bit off the slides. I try to be as clear as possible. The thing is, okay, so all nodes need to have a consistent state, which is bad because then the system is not scalable. Well, it's not scale out, so exactly as Philip said, we will have this constant line of throughput. So no matter how many nodes you have, you will always have a constant throughput. But then, if you want to scale out, you always need to say that a node only needs to acquire part of the state transition records. And we do that by making some assumptions, or let's say we do that by sacrifice a little bit at security or trust or decentralization. So the assumption is that, or either we said there are fewer nodes, fewer malicious nodes than 1/3 of the population, so that we can shard the network securely. Or we said there are a certain group of nodes in this network is more trustworthy than the others, so we can let them to check the validated transactions for us. So by making these assumptions, we remove the redundancy so that the nodes only need to acquire part of the transaction record. Okay, that is also the things that we want to do here. But we want to first look at something called rationality. So let's take a page back from what Nakamoto told us. So in Bitcoin, so why is Bitcoin different from a traditional BFT system? So if someone was here, I think Sarah addressed this problem a little bit yesterday. She said that the Bitcoin and the difference between Bitcoin and BFT, one of the major difference is the incentive. But I think I want to dig a little bit further into that. So what is the main difference between Bitcoin and traditional BFT is that in Bitcoin, we are dealing something which is valuable. We are dealing with money. And people has a very strange behavior when we are dealing with money. And so we always want more money, and we don't throw away money. So basically, in traditional BFT, Byzantine nodes are assumed to perform arbitrary attacks. But when we are dealing with money, our behavior is restricted to a certain pattern. And because of that, we call that rationality. So the assumption be changed from honest node and malicious node to rational nodes. And that is actually what we want to emphasize today, is the rationality. And the rationality, one of the most famous one is that the rational nodes will try to get as many mining rewards as possible. And that's a trick that Bitcoin is playing. And Bitcoin use this incentive as a carrot in front of donkey, so to make miners playing in this solving puzzle game to achieve BFT in a larger scale. But there are some certain other rationalities which has been mislooked, in my opinion, although that we are implicitly using that because we thought that is so trivial, because that's the way we deal with money. And we are trying to point out those rationality. So one of the examples is, why do we pay transaction fee at the first place? I think the clear answer is that we want to make transaction, right? So that's why we pay transaction fee to the miners. We also pay transaction fee to Visa. So when I made the transaction to David, I will send some money to David through Visa, and Visa provide the service of confirming my transaction. That's why we pay him the transaction fee. So if miner is in the place of the Visa, then it's natural that I need to pay a miner transaction fee. But the thing is, why do we need Visa at the first place? So basically, because we want to make sure the Visa help us to make sure that the transaction is confirmed. So basically, David doesn't trust me. David doesn't trust me. And so if I said, okay, I send you some money, and he wouldn't trust me. And actually, he and me and a lot of people in the world trust Visa. So when Visa said, okay, this transaction is confirmed, then David knows that he can securely use this money to send it to someone else. So basically, we need Visa to actually help us confirm the transaction. But the thing in here is that why is I'm paying the transaction fee instead of David paying the transaction fee? Because there is some rationality that we're dealing with value that as a transaction issuer, I am in responsibility of provide him some proof that my transaction is confirmed. And I do that through miner because I send some transaction fee to the miner, and miner put that on chain, and then I send the chain as a proof to David saying that, okay, see, my transaction is confirmed, it is on chain. And then David check the chain and see, okay, so this transaction is indeed confirmed. But the rationality in here is that, okay, as a transaction issuer, I should take responsibility of sending a proof saying that my transaction is confirmed. And then there's another rationality. As a receiver, as David should also check that my transaction is confirmed. And there is a third, the third rationality is gone. Okay, there is a third rationality saying that, okay, so if David has this value, he should actually hold the proof saying that this value belongs to him so that he can use that to prove to someone else that when he makes the transaction. And this rationality, I didn't make up this rationality. I just sum up the rationality people are using in previous works. So, for example, the rationality of value holding, which is not here, says that he will hold the proof. So when he has some money, he should make sure that he can prove the money belongs to him. This thing is basically, in traditional Bitcoin, means that you need to hold your private key secretly. But actually, we are actually extending this assumption more and more. Like in pay-to-script hash, you should also keep a script secretly. And in some other things, for example, in Lightning Network, you should also actively check on the main chain, see if the people send you money is cheating, and you should respond on that within a certain period of time. And that is all falls into the rationality of holding values. So basically, we are not making more assumptions than they should be. We just summarize and formalize the assumptions that people already been made in multiple works. Here it is. Okay, so now we are talking about our system. Before we talk about our system, I will need to talk about my missing slides here. So the things that we are trying to do is the same. So we try to scale out. We try to make sure that the system will still work even without that each node having the whole keep the whole transaction records. But what we are doing here, so what is the cost? What is the sacrifice we make? It's not on centralization, decentralization. It's not on security, but we make a sacrifice on, make an assumption on functionality. So we are design a system for value transfer, and because we are design a system for value transfer, we can use the rationality assumptions, and because of that, we will show that the value transfer can be done securely and decentralizedly, even without, even if nodes only acquire part of the transaction set. Yeah, so the first change we want to make is actually in the name of the value-centric blockchain, is that we do not see the states as a count and balance anymore, but we use some older representations as eCash, so we see them as coins and their owners. That's another way to do to describe a value distribution, right? So at each state there are a lot of coins in the network, and they have owners, and associated with each value, each ownership of value, there is a proof. So basically, if you sum up all the proofs, it is the whole transaction set, because the whole transaction set will prove at each state which coin belongs to whom. But if you separate the whole transaction set, you will have the proof for individual values. And eventually, the system achieve is the last line, is that we will have the system that's rational owner, nodes only need to store the proofs of the values that they own. And even if they don't care about the proofs that other values, they only store the values that the node that they own, but still we can guarantee a secure value transfer because nodes are rational. So how is that done? So the system is very simple. You probably think it's too simple to be true, but yeah, so we call it Vapor. It comes out of the first letter from some of the key elements we use in the system. It's also that I couldn't find a better name, so I just make this out. So the structure is similar to some off-chain schemes. So there is a main chain. We assume the main chain reaches BFT in a certain way. Either it is permission or permissionless. It doesn't matter. It's just a place that people reach consensus on something. And then every node made their own transaction blocks. And periodically, they send a signature of their transaction block to the main chain to reach consensus. And then, when Alice wants to send some money to Bob, what would he do is, what would she do if she's honest? How can she prove that this money is real? It's very simple. So the first thing is that, okay, the money is real when I received it. And here are my transaction blocks, which I didn't spend this money. And then is a green block, which contains a transaction saying that I sent this money to Bob. And then all this, because Alice is honest, she sent all of these things to these blocks to the main chain to reach consensus. And he will send to Bob saying like, look, this is my public key. You can check that all these blocks are sealed, so I cannot change it. I cannot tamper it, and you see that I haven't spent this money and before I send it to you. And this is my proof. And Bob will then put this inside this proof, and then this whole becomes the proof that Bob saying that the money is true when I received it. And so if there is a malicious guy, Charlie, and he wants to cheat Bob, so what can he do? He can either say that this money wasn't real when I received it, so he wants to spend the fake money, or he tried to double spend. So either he sent this money to Bob and later on want to send it to someone else, or he had already sent this money and he now want to make Bob believe that he haven't spent this money before. But he cannot do so because all of these blocks are sealed, and also Bob will check this this proof. And the only thing that Charles can do is basically not showing Bob the proof, but as a rational sender, as I said, why would you like to throw away money? So it's okay. So I think some people will still think this scheme is too simple to be true. So what is the trade-off we are making? So I want to make a theoretical explanation. So with the main chain, how this thing is different from from putting all the transactions on the main chain. The major difference is that in the classical blockchain, if you put all the transactions on the main chain, you guarantee two things, which is the first one is consistency, the second one is liveness. And consistency means that two honest nodes cannot see a transaction in a different way, cannot have disagreement. And liveness means an honest node, if he makes a transaction, it will be known by all honest nodes in a certain period of time. And in our system, because we put the transactions off-chain, we still guarantee consistency via the main chain, because still, like two honest nodes, if they see one transaction, they cannot see it in a different way. But the thing is, we do not guarantee liveness. So there is no guarantee that a transaction would ever be known by all honest nodes. But how can we guarantee liveness is by the rationality assumption. So the liveness is always true between a rational sender and a rational receiver. And we think this is already sufficient for a value transfer system. And okay, so how is this whole system look like? How many time do I have?
You have about 10 minutes left.
Good. Okay, so how is the whole system look like? So as I said, each node only need to hold value of his own proof of his own values. But what is a proof? As I said, if you sum up all the proofs, it will be the whole transaction set. So there are certain. Let's see, these are the transaction blocks, and these are the nodes. So this will be the whole transaction set. And a proof will look like this. So basically, node 1 hold a certain value for two blocks, and then he sends his value to node 2, and then node 2 hold it for 3 blocks and send it to node 3. And at the node 3 point of view, he has these 3 values, so he needs these blocks as all the things that he needs for the proof of his own values. So this looks much smaller than the whole transaction set, right? But I'm cheating here because it doesn't guarantee that the nodes actually will have this. So it could turn out that the nodes will have a certain set of value. Eventually, he still needs the whole transaction set. So our system gives no gain at all over a traditional system. But we can never prove that. So in a very complicated situation, and also like Philip said a little bit about it. So if all the transactions are cross-shard transactions, like in OmniLedger or any sharding schemes, so in a very extreme case, you cannot get any gain, and in our system as well. So if the values are always travels around the whole network, and each node always holds a set of values which all travels around the whole network, then the system will not get any gain. But what we can prove that is in many systems we do gain something. So we do have a more scalable. We can call it scale out, but it has some difference from the scale out that EPFL people has introduced. But the thing is, we allow something called spontaneous sharding. So what is spontaneous sharding? So now node 3 has these 3 values, and he wants to make a transaction to node 5. And which one do you think he will use to send this transaction to? So I think the orange one, right? Because he knows that node 5 already knows the 3 blocks. So if he's rational, another kind of rational, so he will try to minimize his communication cost. And then he will turn to use the values that the receiver that's already familiar with to send the transaction, which means that the values will turn to only cycle in a small group of the node instead of the whole network. And it's equivalent situation as a sharding. So each value forms a shard, and each node will, depending on which values he has, he's kind of participating in different different shards. And this sounds a little bit too fairy tale, like a fairy tale saying that, okay, so if every nodes act rationally, and then we will have a very good world. We have this sharding scenario. And we have this question before. People said, does that fall into the tragedy of the common problem? So do you only achieve sharding when every node works rationally? In fact, it doesn't. So even if all the network is messed up and the transactions always, so the value doesn't form a shard, but it goes through the whole network. But if at a certain moment, me and David said, okay, we make rapid transactions, frequent transactions, let's now start to make a shard. So we only use a certain value back and forth. Then we improve our throughput. So it means that each small groups can always improve throughput by kind of using this rational behavior. And so let's compare it to normal sharding. So as for normal sharding, what we are trying to do is that we artificially divide the shard either randomly or predefined. And then we try to make sure that all shards are secure. And we need some global, well, not really global consensus. Global consensus is the worst case, but we need some additional mechanism to keep inter-shard transaction is secure. So our system is equivalent to that each value spontaneously form a shard. And the shard is naturally secure because all the nodes validate it when they receive the value. And if they are rational, they will do it right. And there will be no inter-shard transactions because basically you transact inter-shard makes that node comes into the shard. And this another advantage we want to address a little bit called decentralization is actually follows what Mustafa has just said. So we want nodes to be able to individually validate a transaction, which is actually not the case for many blockchains, high throughput blockchains proposed recently. So what does that mean? So you can have a consensus algorithm that scales to 10,000 of nodes and it's completely decentralized. You don't need to trust anyone. But if your blockchain actually requires a very high bandwidth and very high performance, very high capacity server, then it means that normal nodes will naturally shut out from the consensus. So I think one very important criteria of the decentralization is the participation threshold. So a node should be able to participate into the blockchain even if they have a low capacity. And in our system, it achieves that. So the most important thing I want to emphasize is the validation thing. So if you only have one value or if you only have 2 coins, you actually has you don't need a lot of bandwidth and storage to validate your 2 coins without relying on any full nodes or any other nodes. You can do that by your own. And I think that is a very good property to have. The last one I want to, it's a kind of okay, this is the last slides. Okay, this is a bit vague phenomenon, but we still want to point it out. It's about the flexibility. So let's assume, let me tell you what would happen if a fork happens in our system. So if 2 group of nodes have a disagreement on the validation of a certain transaction, for example, if DAO instance happens in Vapor, so there are certain transactions that one group want to re-roll and want to roll back. The second, the other group want to proceed. What will happen is that they will have an implicit fork in this system. They will have disagreement on the validity of certain value, and eventually it will fork. But the thing is, both groups will still contribute to the security of the main chain. So later on, in both groups, if you want to do a double spending attack, you still need to beat the majority of the whole population. And I will say this is a very good property, in fact, because you can never prevent people from disagreement with each other, right? You can never prevent that. But in this system, we have a minimum layer of consensus, which is the main chain. And all the higher layer of consensus, you put it in well, let's say off-chain. And then if people have a disagreement on the higher layer of consensus, they can still agree on the basic layer of consensus. I think that is an advantage instead of a disadvantage. And okay, I'll skip that slide, and that's all for my talk. Thank you very much.
Thank you, Jijia. That was very interesting. We have a question right there at the back. Mustafa?
Sorry, I think I might have missed this from your talk, but how did you say that you prevent double spend attacks if if each person is running their own chain with their own transactions? What happens if I do a double spend attack from that?
Excuse me, I didn't catch
you. I think I missed. How do you prevent double spend attacks by using transaction fees?
So how do I prevent double spending attack? So I basically send you a transaction, and you will only believe that I have made the transaction to you when you see that I haven't spent it to someone else. And all of these transactions, you can see from my transaction block, which is sealed by a key that I send to the main chain, which you already have consensus of.
But so every time I spend a transaction, I have to send it to the main chain.
Excuse me?
So every time I want to send money, I have to send my transaction to the main chain.
You need to send a key of the transaction block to the main chain. So no, sorry, not key. A signature signing your transaction block to the main chain to make transaction.
But the transaction block itself, the data of the transaction block, isn't on the main chain, and the block itself could contain transactions that do double spending, right?
Yeah.
So then doesn't that still isn't double spending still possible?
No, because I need to send the block to you, so you will check whether I have spent the money before.
But so then the person you're sending to the transaction to checks your block, but then don't they have to also check the history to make sure there's no?
Yeah, I also send all the blocks that's after I receive the money.
After you receive, no, but don't you have to check the history?
Yeah, the history is actually, the history is basically other people haven't spent the money before.
Okay, but then don't you have to verify the whole UTXO set back to the Genesis block?
Yes.
But then doesn't that effectively, isn't that roughly the same amount of, isn't that roughly the whole UTXO set anyway?
In fact, okay. Well, as this slide suggests, you send certain blocks, but it is not the whole transaction set. But at a certain scenario, as I said, you probably will have the whole transaction set in the end.
Yeah, so aren't you assuming that basically that if you look at the whole UTXO graph, it's not interlinking? So like, if the money is very fungible, and there's lots of people sending transactions to each other.
Yeah, firstly, it will be a little bit different from UTXO because it will not be as fungible as UTXO. And we do not actually know what would happen in real life because it's a very theoretical paper. And also, so the worst scenario is that money got around the world and you eventually need the whole set. Is that your worry? Yeah, but that's something that we can show that under a certain scenario, we got benefit, but we are not sure whether in real life it will have benefit. But we are quite confident that in some scenario it will be better.
Interesting, thank you. Were there any further questions? Yes, here.
So just to add, does the sender decide what blocks to send?
Yes.
Okay.
I think there was one further question at the back there. Microphone's right behind you.
Hi, great talk. Can we follow the developments on this somewhere?
This paper is available online, and we don't have an implementation of this yet. We have an implementation of my previous paper, which is similar to this, but we don't have an implementation of this yet. So it's kind of theoretical work.
Excellent. Oh, Patrick?
Have you read the paper called P-Pay from like the early 2000s? That's sort of similar to this, where you had like a bank, and the idea is that they give me a coin, and every time I spend it to you, I also have to give you the history. And then when you spend it, you show the history of the coin until it eventually reaches back to the bank. Yeah, so the idea with this would be that if I give you the coin, I proved you that I got it from the bank. And then when you send it over there, you prove you received it from me, and then you send it over there as well. But this was only for micropayments because of the chance of double spending.
Yeah, it has a similarity to some older schemes, which is even before the blockchain era.
Yeah, so I recommend reading that paper. That's mostly my point.
Yeah, okay.
Great. Well, if there are no further questions, we will go to a break. We can have a coffee, and I'd like to have you all back here at 12:30, please. of the morning. Our first speaker for the second session is Yue Guo. She is a PhD researcher at Cornell University, and she will be talking to us about Thunder Token.
Someone to collect the people.
I still have a microphone. Okay, sorry.
All right, so if we could all return to the conference area, we'll be starting with Yue Guo.
And perhaps I just start. Yeah. Oh, okay. Hello, everyone. Today I'm going to talk about our improvements of Thunder Protocol and also our proposal of a new synchrony notion. And this is a joint work with Rafael Paz and Elaine Shi. They are both professors at Cornell, and they are also scientists in Thunder Token team. Okay, before talking about anything about Thunder, let me first recap the consensus goal for this public blockchain system. We call it state machine application. So the core value of these public blockchain protocols like Bitcoin, Ethereum, or also Thunder, they want to make these participants agree on an ever-growing linearly ordered lock. And more specifically, we want to have these two properties, the consistency and liveness. By consistency, we mean that honest nodes should agree on the same lock, and once a lock is confirmed, it can never be modified or changed in the future. And by liveness, we mean that if some transaction appears, then it should be included in the lock very quickly. Okay. So Thunderella is a consensus protocol used by Thunder Core. It is a public blockchain platform. And the rigorous mathematical proof is included in the paper by Rafael Paz and Elaine Shi, published in Eurogrid 2018. And in this talk, I'm first going to quickly go through the original Thunder protocol, and then I will describe an attack which can somehow make a confirmed transaction being undone in some case. So does this mean that Thunderella is flawed? And by thinking deeply into this question, we found that actually it is not Thunderella is flawed, it's the traditional synchrony definition actually allows this attack. So here, this leads to our proposal of new synchrony notion. And at the end of the talk, I will also give a fix to the Thunder, which makes it secure under this new notion and gives us better robustness and scalability. Okay, so let me first quickly go through the original Thunder protocol. Let us begin with extremely simple voting process. So this voting protocol runs with n nodes, n committee members. Here are these superheroes, and an accelerator node. Here is the Vitalik. And some of these nodes can be corrupt, like here Loki is corrupt, and the accelerator can also possibly be corrupt. And this voting process has only 3 steps. The first step, the accelerator receives the transaction, and he signs the transaction with the sequence number and proposes this transaction to all of the voters. And next step, on receiving the proposal from the accelerator, every voter will vote for this transaction. By voting, I mean this voter signs the transaction and sends it back to the accelerator. So here, the corrupt nodes can vote for arbitrary things. They can also double vote. They can also keep silent. But the important thing here is that the honest node will only uniquely vote for one transaction that it hears from the proposal from the accelerator. This is important for our consistency proof. And next step, when accelerator collects enough number of votes, the accelerator will pack them into notarization using like BIS signature scheme, and send this notarization back to the voters. And on receiving the notarization from the accelerator, the vote can confirm on this transaction and output it. And this transaction can never be like canceled or undone in the future. So how many votes here are enough for confirm on transaction? Here, if we assume in the whole committee we have honest majority, the notarization requires at least 3/4 of votes. The analysis of consistency is just a very simple application of pigeonhole principle. Like imagine we have two nodes, receive two notifications for two transactions. This means both of them have received 3/4 of nodes, 3/4 of votes, and the intersection of these two sets of voters must have at least 1/2 of nodes. And because we have minority corruption assumption, this means at least one honest node must be in this intersection. And remember that the honest node will only vote uniquely for one sequence number. This guarantees that these two transactions must be equal. So this analysis does not depend on any additional assumption. It only requires honest majority. So here we have consistency with honest majority assumption. But for liveness, perhaps you have already noticed, we need stronger assumption. If we have less than 3/4 of nodes that are honest, or the accelerator might be down or might be corrupt, we might lose liveness because the honest node can never collect enough number of votes and they can never confirm on next transaction and the execution of the protocol gets stuck. So the challenge here is how to achieve liveness. The idea of Thunderella is also very simple. When the things is good, we execute on this fast path, we do this one-round voting process, and if the condition of liveness fails, the execution gets stuck, we can just fall back to a robust slow chain. This slow chain is just any kind of blockchain protocol that achieves consistency and liveness with honest majority assumption. It might be slower, but it gives us robustness. So here you might have two questions. The first one is, how do we detect the failure on the fast path? And the second one is, when we know something goes wrong, how do we fall back to the slow path? So in this talk, I will only give a high-level answer to the first question, and I will focus on the second one. Because the second one, the fallback scheme, is important for us to understand the attack that I'm going to describe later. So for the failure detection, the idea is also simple. When the fast path goes normally, the accelerator just posts periodically the checkpoint of the log of fast path down to the underlying slow chain. So this, we call it heartbeat, and it can be seen by all of the committee members. But when something goes wrong, enough number of committee members will notice that for a long period of time, there are no more new heartbeats. Then these committee members will stop participating in this fast path, and they start to fall back to the slow chain. Okay, now I'm going to talk about the fallback scheme. The challenge here is that when these committee members decide to fall back, they might have different view of the fast path log due to the network delay or corrupt accelerator. Like here, the Spider-Man only sees a subsequence of the log of the Iron Man. Okay, so the challenge here is that they need to agree on the fast path only with this slow chain. The idea is that we can post all of our notarized but uncheckpointed transaction onto the slow chain. Because the slow chain guarantees consistency only with honest majority assumption, this guarantees that any transaction that I output on the fast path will finally appear on the slow chain, which means every others will also output it. So do you have any questions about this part? Okay, so as a conclusion, the Thunderella achieves the following two good properties. In the optimistic case, it can confirm a transaction only with one voting attempt. And if things goes bad, it can always fall back to a robust blockchain protocol and get at least the performance of the underlying blockchain. And whenever the nodes reach consensus on the underlying slow chain, they can always re-elect the accelerator and the committee members to rebootstrap the fast path. So 99% of time, the protocol will run on the fast path and can confirm transaction in 2 or 3 actual network rounds. Okay, so it sounds good now. We have consistency, have liveness, we are efficient, we can confirm the transaction very fast. But as I said, I'm going to describe an attack that can actually get some confirmed transaction being somehow undone And in this attack, even no nodes are doing any malicious things. The only thing required in this attack is that some nodes drops offline in a specific timing manner. So does this mean the Thunderella is flawed? Let's take a look together. Okay, so this attack goes like this. The first step is the same. The accelerator proposes the transaction and the sequence number to all of the voters, and the committee members will vote for this transaction. They send this vote back to the accelerator, and the accelerator collects enough number of votes, and he will send this notarization back to the, all of the voters. But unfortunately, let's assume Coinbase is it's the first node that received this notarization. But unfortunately, the accelerator drops offline immediately after he sends this notarization to the Coinbase node. So here, Vitalik drops offline, and at this time point, Coinbase is the only one who sees this notarization. Okay. So as I described, Coinbase will just output this transaction and think it is confirmed, and he tells Patrick, "Hey Patrick, someone sent you a bunch of money and want to buy you a Ferrari car," and Patrick think, "Oh, okay. Coinbase says this transaction is confirmed. I'm happy to deliver my Ferrari car." So Patrick delivers his Ferrari car, and makes things worse. At this time, Coinbase also drops offline. So what does this mean? Coinbase is the only one who knows this notarization, and no one else sees this notarization. And Coinbase drops offline. Not any nodes online knows this notarization or this transaction is confirmed. So as I said, all of the other nodes will find that the heartbeats stop, and they will start fall back to the slow chain after a while. And what they're supposed to do here is they put all of their notarized transactions onto this slow chain so they can get consensus. However, at this time point, Coinbase is also supposed to put this notarization onto the slow chain, but because he's offline, he fails to do so. So when Coinbase comes back online after 1 day, all of the other nodes have rebootstrapped the fast path, and the notarization of this transaction has not appeared on the fast path, on the slow path. So what happens here is that no one else sees the notarization, and no one else includes this transaction into their log. So this transaction is somehow being undone by all of the other nodes. So now Patrick lost his Ferrari car, and he don't receive any payments, so only thing he can do is just crying. Okay, so this sounds horrible, right? It looks like the protocol is flawed. Coinbase node does not do anything malicious. Perhaps the Coinbase doesn't even know he's offline for a short period. But even if I come back online after a short while, I lose all of the consistency from the other nodes. So how can a protocol allow this kind of horrible behavior? Does this mean the protocol is flawed? And if you think it is flawed, so what about that 74 pages of security proof in a Eurocrypt conference, which is a top-tier crypto conference? Does this mean the whole security proof is also wrong? So by thinking deeply into this question, it turns out that actually the proof is not wrong, and the protocol is also allowed to have this undesired behavior. This actually is inherently allowed by the classical synchrony model. So what does it mean by we have a synchronous model? In a synchronous network, we assume that all of the honest messages will be delivered or sent in only one round. If any node fails to satisfy this assumption, this node will be considered malicious or not malicious, will be considered corrupt or failure. So if I just drop offline for past only one round, I don't deserve any consensus anymore. So does this part make sense? Okay. So perhaps you are thinking that I'm not talking about anything new, because this is just the assumption of synchronous network, and this is actually why people use partial synchrony in some scenarios. So partial synchrony is having this very loose assumption. It's saying that the message delay can be as long as you want, and in this case, the temporary outage can be just regarded as a long message delay. So no matter how long you wait, whenever you receive the message finally, you will get the consistency with the other nodes. So why don't we just use partial synchrony network rather than use synchrony? The problem here is there is a long-existing and well-known upper bound saying that any protocol that's secure under partial synchronous assumption can only tolerate less than 1/3 of corruptions. On the contrary, in a synchronous network, we know a bunch of consensus protocols that are efficient and tolerating minority corruption assumption. And moreover, if you don't care about running a protocol for a very long time, for many, many rounds, you can even get a protocol that tolerates arbitrary number of corruptions, like $strong. So, an interesting and natural question here is it possible to achieve the best of both worlds? Can we both have these, we don't regard these temporary offline nodes as faulty, and we can still get this better resiliency? So, at the first glance, the answer of this question might be impossible, because to circumvent that 1/3 lower bound, we rely critically on the timing assumption, that one-round timing assumption of synchronous network. So how can we circumvent the lower bound without assuming the message can be delivered very quickly? But the interesting point here is, who says that the network must be either synchronous, must be either fully synchronous or not synchronous at all? So who says that the synchronous status of a network must be a binary choice? So can we quantify the status of the network more accurately to find that if there's any trade-off between these two models? So let's consider a more natural network condition in practice. So in most cases, we have a bunch of nodes that are honest and they are well connected. They have this strong network signal. But we also have a small set of nodes that might experiencing short-term outage. They might be offline for a while. They might have unstable connection. And we also have some corrupt nodes who can behave arbitrarily. So on the synchrony network is saying that I don't care about that gray set. All of them, I just consider them as faulty. And the partial synchrony is assuming that all of the nodes are in the gray set, and it does not make use of the good connection of this green set. So what we want to do is to take the size of this green set into consideration and to see if in this case we can guarantee consensus for the green nodes and the gray nodes. Okay, so does this part make sense? Do you have any questions? Okay. Okay, so answer to this question actually includes two parts. The first one is, if this green set is too small, then our conclusion is that it's impossible to reach consensus between these sets. This conclusion is like intuitive because you can imagine that you have two partitions in the network who are both well connected internally, and they are not connected between each other. So how can they reach the same consensus if I only have like two small partitions? But if the network condition is better, if we have more than half of nodes are well connected and the message for them can be delivered very quickly, we can actually guarantee consensus between these green nodes and the gray nodes. So actually, I'm going to talk how to fix the Thunder protocol that I talked about earlier, to make it guarantee consensus in this case, and how we can even do better, reach a stronger notion that we can guarantee consensus in a more dynamic network. Like here in this graph, it looks like this green set should be static, like all of the nodes that once online should be online from the very beginning to the end of the protocol. But with Thunderella, with the fix, we can actually guarantee consensus as long as at any time point, this green set is large enough. So which means we tolerate more network churn, like the nodes can come and go, can be online and offline, as long as at any point, the set of these well-connected components is large enough. So does this part make sense? Okay. So we also call this notion best possible partition tolerant because, as I said, if we only have the green set less than 1/2, we cannot have such a protocol. So 1/2, more than 1/2 is the best partition tolerance that we can achieve. So next, I'm going to talk about how to make Thunderella best possible partition tolerant. Actually, this fix also contains 2 parts. To make the whole protocol partition tolerant, we need to have both fast path and the slow path to be best possible partition tolerant. And because the fix to the slow path is a little bit tricky, I'm not going to the detail of how to fix the slow chain, but I will focus on the fix to the fast path, and it will be extremely simple. Okay, so assume that every honest node only vote for some transaction after they see the notarization for the previous transaction, which means now I will only vote for that blue transaction after I see the notarization for all of the golden transactions. This is a precondition. And now on the fast path, we need to chop off the last notarized block, the last notarized transaction. Sorry, I use block like interchangeably. And I only output the whole prefix without the last transaction. And when we fall back to the slow chain, we actually put all of the notarized transaction down to the slow chain. So there are only like 2 simple steps. We can make this protocol partition tolerant. So why this works? It is still a very simple application of pigeonhole principle. I only output golden transaction after I see the notarization for the blue transaction. The notarization for blue transaction actually contains more than 3/4 of votes. So this means more than 3/4 of nodes have already seen the notarization for the golden transaction. As we assume, they will only vote for this blue one after they've seen the notarization for the golden ones. And because we have this, in this best possible partition tolerance model, we assume that in any round, there are more than 1/2 nodes are online. So when the fallback happens, there will also be more than half of nodes that are honest and well-connected. So there must be some nodes in this intersection. They are both honest, they are well-connected, and they voted for this blue transaction. So this part of nodes will guarantee that they know the notarization for all of the golden transactions, and they will put these golden transactions onto the slow chain. So the core idea here is that I only output some transaction when I know that some nodes will put the notarization down to the slow chain, even if I drop offline. I know some online nodes will do this for me, and I know enough number of nodes in the network have already seen the notarization, the same notarization I have. So does this part make sense? Or do you have any question about this proof? Okay, so actually this is the whole fix of the fast path. And though I'm not going to talk about the detail of the fix to the slow path, I want to mention two interesting points here that we found when we tried to design the fix of the slow path. The first one is that the best possible partition tolerant notion is actually turns out to be a refinement of honest majority notion in the classical synchrony network. So, but we investigated a bunch of protocols that work in classical synchrony with honest majority assumption. All of them do not satisfy the best possible partition tolerant, which means they are just like the original Cinderella. They cannot tolerate any nodes become offline and back online again. So Cinderella is actually the first one in this area. And the second point is that the traditional synchrony notion is somehow misleading because in a classical synchronous network, we tend to think that if protocol tolerates dishonest majority, it is more robust than the protocol that only tolerates honest majority. Like the more corruption you tolerate, the more robust you are. This is like intuition in the classical synchronous network. However, it turns out that any protocol that tolerates dishonest majority cannot be best possible partition tolerant. So these two sets must be are disjoint, which means sometimes the more corruption you tolerate does not mean that you are better in this robustness area. Okay, I think so. Here are the 2 points. And as a conclusion, in this talk, I first quickly described the Thunder protocol, and I described an fake attack. And then I propose a new best possible partition tolerant notion, and I give a fix to Thunderella, which gives us better robustness and make the Thunderella can work on a larger network. This gives us better scalability. Okay, thank you very much. So please, I'm happy to. Thank you.
Great, thank you, Yue. That was really fun. Who has? We have a question right here. You're right in the middle, so.
Thanks for a great talk. I was wondering what happens if the 1/2 honest nodes kind of lose their well-connectedness and temporarily are not well-connected anymore. Do you lose only liveness, or do you also lose the safety property?
Sorry, let me repeat your question. So you mean if some honest node get offline, and will it lose liveness or also consistency?
Yeah, if you have, you typically assume like 1/2 honest, well-connected.
Yeah.
And if temporarily you don't have the 1/2 well-connected honest nodes, but say less than that.
Actually, so as I said, it is a refinement of synchrony, which means we still use the assumption that the message can be delivered very quickly in the majority part of network. So if in some round less than 1/2 are online, then this protocol, let me think. I think it can lose consistency. Yeah, it's still a synchronous assumption.
Right. Were there any further questions regarding this presentation? Otherwise, we will move swiftly on to the next presentation. So thank you.
Okay, thank you.
Our next speaker is Fisher Yu, who is an engineer at Dolby Laboratories, and he's going to talk to us about polyshard and coded sharding.
Okay, Okay, just in case you don't know, the lunch will be served after my presentation. So I will guarantee you I will make my presentation as succinct as possible. So for one, I'm as hungry as you, and second, my computer is also very hungry. My battery can only last for like 30 minutes. Okay, cool. So to start with, I would like to introduce myself a little bit and do a housekeeping statement. So my name is Mingchao Yu. You can just call me Fisher. I did my PhD in network coding and information theory from Australian National University. So anyone here from the South Hemisphere? No? Okay, then I'm unique. Yeah, and then last year I joined University of Southern California and did works on distributed computing with Professor Salman Eversmere. And recently, I joined Dolby Laboratories because Dolby acquired a startup company I worked with, and as the inventor of all the patents, I am part of the deal. So the Polyshard work I present today has nothing to do with Dolby at all. It is my work did with my colleagues in USC, Dr. Sunze Lee, and Professor Salman Eversmere, and collaborators from University of Washington, Professor Sriram Kannan and Professor Pramod Viswanas from UIUC. Okay, so all of us has an information theory background. So when we did our literature review on blockchain and try to understand its scalability, we found that sharding is a very promising and interesting solution with certain trade-offs. Then our information theory minds shout out that, wait a minute, these trade-offs can be solved using information theory. Then here it comes, Polyshard, which is the very first sharding proposal that tries to scale blockchain from the information theoretical perspective. Cool. So the outline of my... Really? They will go backwards. Let me try it. Yeah, it did work. But never mind, I can use my keyboard. Yeah? Yeah, that's fine. Okay. Time is clicking. Okay, so the outline of my talk today. So first, I will show you the storage and verification model we are considering and define the performance matrices we are interested in. Little spoiler, we consider security, storage, and transaction throughput. And then I will discuss the scalability of two existing blockchain solutions. And then I will introduce Polyshard step by step, and then summarize my talk. And after that, I will spend 1 minute to talk a little bit about our team and our other works. Okay? So, first, excuse me.
Would you like?
Yeah, will be great. Thank you. Hope they will not confuse things. Yeah, it works perfectly.
It even has a laser. Try not to.
Point to myself. Okay, never mind. So, what we consider is a verification function that involves a ledger and a transaction block and a verification function. So what each node does is it has a ledger, and when transaction comes in, it runs a verification function and make decision, so whether this block is valid or not. Okay? And then the performance matrices we consider, there are three. The first is storage efficiency. We measure how much data or how large is the ledger stored in each node. Because we want it to be larger, the better, so we take its inverse. So it's 1 over the storage size per node. The second metric is throughput, which is the number of transactions we can verify per epoch. The third measure is security, which is the number of malicious nodes this system can tolerate. And here, we will consider quickly adaptive adversaries, which means the adversaries can quickly figure out which node belongs to which shard and do some dedicated attack. Cool. Now, we look at the performance of the black screen. Okay, so first, the classic blockchain system, without any sharding, we call it a full replication system because, say, we have 30 nodes, then every node will store the whole ledger, and that when the transaction is received, every node will do the verification. Then there are some consensus going on afterwards. For this system, its performance is as follows. Its storage efficiency is 1, because every node stores the same thing, so it's O1, it's a constant. Throughput is 1 block per epoch, which is also constant. But its security is that it can tolerate at least half of the nodes to be malicious. So its security is in the order of n. To be precise, it is n over 2. That means for the classic blockchain system, if you increase the number of nodes, its storage will not reduce, its storage cost won't reduce, its throughput won't increase. It's only that its security will increase. And actually, in real-world system, if you increase the number of nodes, actually the throughput might even reduce. Then here comes sharding. So given, say, we have 30 nodes, and we would like to have 3 shards, say, the Netherlands shard, the German shard, the Belgian shard. Then what we do is for the 30 nodes, we assign 10 nodes each for each shard. And then so when transactions of each shard come in, or the 10 nodes of the corresponding shard will take care of the verification. For such a system, so we assume there are q nodes per shard, and the number of shards is k equal to n over q. In here, so q is equal to 10, we have k equal to 3 shards with a total of 30 nodes. For such a system, what is its performance? Yeah, cool. So its storage efficiency is 1 over k ledger per node because we partition the whole ledger into k pieces. So each node only stores 1 over k fraction of the ledger. So the storage efficiency is in the order of n. It increases linearly with n. The throughput is k blocks per epoch because we have k blocks coming in for the k shards. The problem is its security. Because each shard is only handled by 10 nodes, then if I corrupt 5 nodes of this shard under a quickly adaptive adversary model, then this shard will be compromised, which will ruin the whole system. So the security of this system is only O1. It doesn't scale up when we increase the number of nodes in this system. Okay? So in summary, we have a dilemma here. If we use full replication, then we have the highest level of security, but our throughput and storage do not scale. But if we use sharding, then our storage and throughput will scale, but we sacrifice the security. So there is a tension between our security, storage, and our throughput. So in order to solve this tension, we will introduce Polyshard, step by step. So our first step is to look at the storage side of the whole system. There actually exists a very handy rapprochement between the storage and the security, which is as follows. So let's consider a system consists of 6 nodes. If we use the full replication system, then every single node stores the whole copy of the ledger. It has the highest level of security, but the storage efficiency is poor. Okay? Then if we use sharding, then what we do, suppose we have 2 shards, then we partition our ledger into 2 pieces, say subledger A and subledger B, and we use 3 nodes to store subledger A and use 3 nodes to store subledger B. This one has a better storage efficiency than the full replication, but its security is a bit concerned, because if I attack 2 nodes that stores the ledger B, then there's no way we can make consensus of what's the value of B. Interesting enough, for such a system, there is a very handy solution to achieve storage efficiency and security simultaneously. So if you are familiar with coded distributed computing or anything like Reed-Solomon code, you should already know the solution, which is as follows. So we treat subledger A and subledger B just as 2 giant vectors under some certain field, certain finite field. And in each node, what we store is a linear combination of A and B. So the size of A plus B is equal to A and also equal to B. So it's just a linear combination. So in node A, we can store A plus B. In node 2, we store A plus 2B. In node 3, we store A plus 4B, so on and so forth. So this is actually a Reed-Solomon encoding of the different portions of a whole file. Okay? So under this system, no matter which 2 nodes you compromise, there are still 4 other good nodes that store the true value of linear combination of A and B. So as long as any 2 of them survive, you can recover both A and B. And if more nodes survive, then you can detect the compromised nodes or even correct them. So by using, this is something called redundancy coding in information theory. So by applying redundancy coding on the storage, we can enjoy both storage efficiency and the security. So storage and security can get along with each other through redundancy coding. What about throughput? Do you think throughput can also be scaled using redundancy coding? So what's wrong with throughput? You might think, okay, this thing doesn't work for throughput because once you mix or create linear combinations of the different shards, then the coded subledgers cannot be used to verify transactions, right? Because when you have subledger A, you have the balance of each user, which is understandable. But if you combine the balance of people from shard A and shard B, what's the value stored in that vector? It's not comprehensible, right? So you might think throughput or the verification cannot be done after we encode the subledgers together. But the reality is, no, that's not true. It is still possible to do verification even if we encode the shards. So the key to realize this is something called coded verification or coded computing. So I will introduce coded verification using a very simple toy example here. We consider a very, very simple verification function where R is equal to B minus K, B minus X, where Bx is the current balance of all the users in shard K. And Xk is the fund that all the users in shard k will send out in this epoch. And Rk is the remaining balance of each user after all the transactions get approved. So this block will only be valid if the remaining balance of every single user is greater or equal to 0 after this xk get approved. So our verification function is current balance minus the money to be sent, and we track whether the resulted balance, remaining balance, is greater or equal to 0 or not. Okay? So this is our verification function. Now we consider a system that has 6 nodes and 2 sharding. That means we will have shard 1 and shard 2. So say we use node 1 to 3 for shard 1, then all these 3 nodes will do the same thing, which is the current balance B1 of all the users in shard 1 minus X1, which is the submitted block for shard 1, and calculate R1. And then they make consensus to see whether this block should be approved or not. And then similarly, node 4, 5, and 6 will all work on the second shard to calculate R2 equal to B2 minus X2 and make consensus to decide whether we should accept X2 or not. Then the problem is obvious. If I compromise 2 nodes in shard 1, then shard 1 is compromised. Okay? Now, we have a new idea. So what we do is every node has a linear combination of both the ledger B1 and from shard 1 and B2 for shard 2. So see, the balance here is B1 plus B2, B1 plus 2B2, B1 plus 4B2, just as what we just showed for the storage. And also, for the incoming transaction blocks X1 and X2, we apply the same coding. So node 1 has X1 plus X2, node 2 has X1 plus 2X2, node 3 has X1 plus 4X2, so on and so forth. So each node has a linear combination of the balance of all the shards, and it also compute a coded block, which is a linear combination of all the blocks from each shard. And the result, the remaining coded balance is, as you can see, node 1, its computation result is R1 plus R2. Node 2's result is R1 plus 2R2. Node 3, the result is R1 plus 4R2, so on and so forth. As long as any two of them survives, we can recover both R1 and R2. So to achieve this, the nodes, once they finish their own computation, you just share with each other their coded results, and then they apply decoding, which is basically solving linear equations, to find out both R1 and R2. And this system is robust as long as any no more than 2 nodes get compromised. So this is a toy example of coded transaction verification. At a high level, what we do with coded computing is as follows. So we have a function f, which takes a vector x as input and an output vector y. We would like to evaluate this function for k times. So y1 equals to fx1, y2 equals to fx2, and up to yk equal to fxk. So in a traditional way, what we will do is we will find k nodes and assign each x to each node and ask them to compute the corresponding y1 up to yk. In sharding, what we do is we assign multiple nodes for each computation task. But in coded computing, what we do is as follows. So given all the k inputs, x1 up to xk, we create n-coded inputs and assign these n-coded inputs, which is w1 up to wn, to to n different nodes. And these n nodes will compute n results. It turns out that the encoded results here are actually linear combinations of our desired y1 up to yk. So the core of coded computing is to inject redundancy to the input so that the output at all the nodes, they are linear combinations of our desired outputs so that we can decode our desired output through linear decoding. Okay? So in order to achieve this, my colleagues Yu Chen invent a coding technique called Lagrange coded computing, which is the algorithm that achieves such coded input leads to coded output property. And this algorithm works for any function that is a multivariant polynomial function. So what we do is as follows. Given the k inputs, we create a polynomial that pass all these k nodes. And then the coded inputs are some randomly picked values from this polynomial. So if I use animation, so we have the k inputs, we find out a polynomial that pass all these nodes, and then to create the coded inputs, we just pick some n random points in this polynomial. And because both x and w are belong to the same polynomial, if we drop them into a polynomial verification function, the output, coded output z and our desired output y, they actually also belong to the same polynomial. So in terms of decoding, what we do is as follows. So each node will do its computation, and we gather its output, which are some points in this chart, z1, z2, z3, up to zn. Some of them might be missing, and some of them might be wrong. So based on these points, we find out the polynomial. See, so some of the values are correct, some of the values are wrong, and maybe some of the values are missing. But as long as there are enough correct outputs from the nodes, we can recover the polynomial. And our desired y1 up to yk are actually the evaluation of this polynomial at its first k inputs. So this is Lagrange coded computing that allow us to create a redundancy for the input and obtain a redundancy at the output, which allow us then to decode stuff. So how will coded sharding looks like if we apply such redundancy? Now, imagine we still have 30 nodes and 3 shards. Now, each node here will store a coded copy of all the 3 subledgers. And when the 3 transaction blocks are received for all the 3 shards, each node will compute a linear combination of all the 3 blocks and then apply the verification function. Once they finish the computation, they will share with each other their results so that each node can apply polynomial decoding to recover all the function results, which is the output of the verification function. Then you can decide whether each block is valid or not and to include them. So in more mathematically, what happens is as follows. So whenever, in each epoch, we receive k blocks from the k shards, then each node creates a linear combination of all the k blocks and create a coded input to the verification function. Then you pass the verification function, the input to the verification function, and then it will share with each other the verification result. And then once each node receives all the output of all the nodes, it will decode the decision of each shard and then create a linear combination of all the valid blocks and include it in its own chain. So the chain stored in each node is also coded. So it's the coded version of a ledger. Okay. So main theory is the performance of Polyshard. So given a blockchain system with n nodes, and μ% of them are malicious, and the verification function has a degree of d, then our Polyshard can support k equal to this many shards, which is linearly to the number of nodes n. And its storage efficiency, it's also a function of the number of nodes, the degree of the verification function, and the malicious percentage. And it is also linearly to the number of nodes n. Also, its security is similarly a function. It's linearly to n. So in summary, full replication achieves a linear scale of security, but not storage and throughput. Our uncoded simple sharding achieves storage efficiency and throughput scaling, but not the security scaling. But Polyshard can achieve linear scaling of both storage, throughput, and security. And it turns out that from information theoretical point of view, this is the best you can do when your number of nodes increase in a system. So Polyshard allows all the three performance matrices we consider to scale linearly. And we also did some simple simulation to test the performance of Polyshard. So the verification function we use is what we just mentioned in the toy example, where we look at the current balance of each shard and subtract the money to be sent and look at the remaining balance of each sender to see whether the block is valid or not, based on whether all the sender will have a remaining balance of greater or equal to 0 after the transaction. Okay? And we plot the throughput of Polyshard, the full replication, and sharding against time and against the number of nodes in a system. So as we can see, when time goes, our epoch increases, our train length increases. So the time it takes to calculate the current balance will increase, and that's why the throughput of all the schemes will reduce over time. But we always achieve a gain of 50x, which is the same as simple sharding, because we have 50 shards. And when the number of nodes increase linearly, we can see the throughput of both Polyshard and uncoded simple sharding increase linearly with the number of nodes, while the full replication, the classic system, its throughput is a constant. Okay? So summary and future extensions. So from information theory perspective, replication is an inefficient way of doing redundancy coding. So full replication sacrifices the storage and throughput scalability, and the replication within each shard will increase the storage and throughput scalability at the cost of security. But in Polyshard, we will use polynomial redundancy coding for coded storage and coded computing, so that it will achieve the optimal scaling of both throughput, storage, and security. And so far, our polynomial Polyshard supports any verification function that is a polynomial. So our development is still in early stage, so there are tons of future works we plan to do. For example, we will try to support the cross-shard transactions, to support non-polynomial verification functions, and to improve our polynomial encoding and decoding efficiency, and to improve our efficiency under network dynamics in synchronized and asynchronized settings. Okay, so that's all for Polyshard. So before we go for lunch, please excuse me for 1 minute for me to describe our team and some other works. So this work is done under a startup company called Applied Protocol Research, which is staffed with renowned academics from different universities with various backgrounds, including Andrew Miller and David Shea, which is kind of the father of information theory. And also my supervisor, Professor Salman Avasmia. So Polyshard is one of our attempts to scale the blockchain. So the other project we are currently working on is called Prism. So at high level, the Prism protocol, it is a DAG-based protocol system, and it deconstruct the blockchain by separate the different functionalities of the blockchain, like verification, transaction proof, block approve, leader selection, and voting into different parallel functionalities so that all of them can run in parallel. The result is remarkable. So when the adversary power increases, its throughput actually decreases linearly with the capacity of the channel. So when there is no adversaries, the Prism system can process transaction which is equal to the bandwidth that the number of transactions the network can allow to be delivered. So its throughput decreases linearly with the adversary power, which is optimal. For latency, it's when the security parameter increases, its latency is constant up to a point, and its latency increases slightly after a certain point. But on the other hand, the current Bitcoin system, its latency will increase very quickly at a very much earlier stage. So this is the other work we are currently working on. So that's all from my talk. So if you have any question related to Polyshard, you can contact me. For the team, you can contact Professor Pramod Viswanas. Okay, thank you very much.
Excellent.
Yeah.
Thank you, Fisher. That was really interesting. We have time for a few short questions. Mustafa?
Could you clarify, so are you applying the sharding per block, or are you sharding the entire state of the blockchain in like one big coding?
Yes, so we shard the whole blockchain and apply coding. Each node will not only take care of its own shard, it will take care of all the shards through coding.
Right, so you have like one big code and you update that code every single update,
What do you mean by update?
Every time the state of the ledger changes, you update that code.
What do you mean by herd? The herd is all the nodes?
No, by the state of the shard.
Yep.
So you have a big code per shard, and do you update that code every time a new transaction comes through?
Yes.
Okay. So with recent sharding proposals, the consensus nodes in the shards, they're not responsible for storing any of the state in the shard, because they effectively run stateless clients. And so the job of actually storing the state and the storage is basically anyone who wants to run a full node, anyone that wants to validate the blockchain, but they don't have to be part of the consensus. And that's necessary because if you keep reassigning those to shards, then you can't have nodes download the entire state because it's not really sharded anymore. So my question is, do you think that this could potentially be applied, this sharding scheme and verification scheme could be applied to clients or full nodes that are running independently and verifying the blockchain, as opposed to the consensus nodes in the shard themselves?
Yes, so currently we only consider the full nodes, which can get access to all the shards and all the blocks. We currently do not consider the clients.
No, I mean, by full nodes, I mean clients. So to clarify, I mean, you're sharding among the consensus participants in the shard, right? But in recent sharding proposals, the nodes in the shards that are participating in the consensus, they don't store any state. They basically run stateless clients. So there's no need to apply sharding there's no need to shard the storage for the consensus nodes. Instead, it's simply the clients, the end clients, that store the state. So my question is, could you adapt this system in the future to apply the polynomial encoding, the erasure coding, to the clients, so that clients only have to store part of the data to be able to verify transactions?
Yes, I think so. I don't see any problem there. Yeah.
Cool.
Hi, Philip.
Hi, thanks for the presentation.
Yeah.
I was wondering which kind of verifications I can perform. Like, for example, to add to your toy example, you check that the balances match up, but could I also check that the signature, for example, is correct or something like that?
Yes, good question. So currently we only support verification functions that are polynomial. The classic signature verification functions such as the elliptic curve ones, they are not polynomial. So there's no native support to them currently. But the good news is there's something we can do is come on. Okay, anyway, so there's a recent paper showing us that any function that works on the binary field can be extended to a polynomial over a higher field. So that means if we want, we can convert literally any function into a multivariant polynomial function and then drop our polyshard on top of it. But that is kind of inefficient because you do field extension, which is very time-consuming and costly. So we try to work out the polynomial sharding that natively support non-polynomial functions, as I mentioned in the future work.
Are there any further burning? Okay, all right, let's do it.
Yeah.
There's a microphone in the back. Thank you.
Yeah, I have a question. So the way where I see like the problem in the network, it's not the size of hard drives that's limiting, it's the network throughput. Like we're limiting block size not because our hard drives are full, but because network latency and sort of uncle rate or whatever you want to call it. So my question is, your scheme seems to need every node to get all the blocks from all the shards. So yes, they only store 1/k of the state. So they save on hard drive space, but we're not saving on bandwidth at all. So because every node to calculate its linear combination needs all the blocks from all the shards, isn't that really the limiting factor that we need to minimize rather than the storage requirement?
Yes, so communication cost is something we pay for polyshard because in order to encode all the shards, then you need to download
all the blocks.
initially. But later you don't have to download all the K shards.
No, but like on an ongoing basis, you always need all the blocks from all the shards in order to...
Yes, all the blocks, yes.
Yeah.
Yeah, but one way to accommodate this or to alleviate this problem is to do sparse coding. That means you don't encode all the shards, you only encode like, say, 10% of the shards, all the blocks, so which will reduce the bandwidth consumption. So currently we encode all the blocks from all the shards, but there are sparse coding that we don't need all the blocks. Yeah, but yes, communication cost is something we pay in polyshard.
Thank you. All right, great.
The more the merrier, please.
Of course.
If a shard gets corrupted, and you have a cross-shard transaction, how would you avoid the breaking safety?
Okay, so far we haven't looked into cross-shard transaction yet. Yeah. So I can't answer the question for now.
Yes, a quick question. Maybe this is obvious, but so you're with your balance checking mechanism. You said that you're basically checking that the transactions. Sorry, I'm not pointing at anything. Transactions in the block are not spending more than the value in the shard. But doesn't that only prevent someone stealing more money than there is in the shard? But it doesn't validate it on a per transaction basis. So couldn't a user still submit a transaction that spends more money than they're allowed to, but not more money than exists in the shard? Sorry?
I'm not sure whether I get your question correctly. Could you please repeat?
Yeah. Okay. Does your balance checking mechanism prevent users invalid transactions on an individual basis?
No, it will verify them as a block. So if one transaction is invalid, then the whole block will become invalid.
But I thought you said your balance checking mechanism checks if the value of all the transactions in the block is greater than how much value there is in the shard. So
yeah. So every client's remaining balance. Yeah. Not the sum.
Oh, okay. I see.
So every single user's balance must be positive or non-negative after the transaction, not the sum of them.
Oh, I see. Thanks.
Yeah. Great.
Thank you. So clearly this has sparked a lively discussion, which is great. Fisher will be here also during the lunch break and for the rest of the afternoon. So if you have further questions, please feel free to ask him. We're going to break now for lunch, and we will reconvene at 2:30.
Okay. Thank you.